Hey everyone, and welcome back to my channel. Have you ever wondered what secrets hide in the icy hearts of comets? Today we're diving into one of the most fascinating cosmic mysteries of our time, 3I Atlas, an interstellar comet that zipped through our solar system in 2025, leaving scientists stunned by its toxic cargo, cyanide and nickel. What do these deadly elements reveal about the birth, death and rebirth of stars? And how does this comet connect to our own origins? Let's explore. Discovered as the third interstellar visitor ever detected, 3I Atlas isn't your average comet. Born in the distant Milky Way, it hurtled past our sun at breakneck speeds, its glowing coma spewing gases that hint at violent stellar nurseries and ancient cosmic collisions. But why should we care? Because the cyanide and nickel in its tail aren't just poisons, they're cosmic fingerprints, telling stories of supernovas, red giants and the recycling of matter across galaxies. In this video, we'll unpack everything you need to know about 3I Atlas. First, we'll meet this interstellar traveler head-on. What makes it different from comets born in our own solar system? Then, we'll decode its hyperbolic escape route, a physics-defying trajectory that proves it's truly from another star. Next, we'll zoom into its anatomy, breaking down its icy nucleus, toxic coma, and sprawling tails, and explain how telescopes like Hubble and JWST uncovered its secrets. But the real drama begins when we ask, where did 3I Atlas come from? By tracing its path through the Milky Way, we'll journey into galactic archaeology, uncovering clues about its ancient, possibly pre-solar system origins. Along the way, we'll compare it to famous interstellar visitors like Oumuamua and Borisov, and even debunk wild theories about alien involvement. Finally, we'll tie it all together, how this comet's toxins mirror the very elements that built our planets, our oceans, and even our DNA. Whether you're a space enthusiast or new to astrophysics, this video will show you how a single comet can rewrite our understanding of the universe. So hit play, subscribe for more mind-bending science, and join us as we follow the trail of nickel and cyanide to the heart of cosmic evolution. Let's go. Imagine a traveler from the furthest reaches of the galaxy, unmoored from the gravitational embrace of any single star. 3I Atlas is such a visitor, a comet that has traversed the vast emptiness of interstellar space for untold millennia before brushing against the edges of our solar system. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this interstellar wanderer carries with it the raw materials of distant worlds, carbon dioxide, water ice, and traces of cyanide and nickel. These are not mere chemical curiosities. They are signatures of a history written in the crucibles of ancient stars, in stellar nurseries where planets were born, and in supernovae that scattered elements across the cosmos. Why does 3I Atlas matter? Because it is a relic of the Milky Way's past, a messenger bearing fragments of a time when stars and planets were still forming, and it offers us a glimpse into the universal processes that shape not only our own corner of the galaxy but countless others. Unlike the comets that originate in the Kuiper belt or the distant Oort cloud, 3I Atlas is not bound to the sun. Its hyperbolic trajectory, a path so elongated that it curves outward into the void, confirms its extraterrestrial origin. The sun's gravity, powerful as it is, cannot hold this traveler. Instead, 3I Atlas continues on its journey, destined to exit the solar system forever. Yet during its brief passage, it has become a focal point for astronomers and planetary scientists, eager to decipher the secrets it carries. What can its composition tell us about the conditions in its home star system? How did it escape its native world? And what forces propelled it across the interstellar abyss? These questions, and the answers we seek, lie at the heart of humanity's quest to understand the cosmos. 3I Atlas is the third interstellar object confirmed to have visited our solar system, following the enigmatic 1I Oumuamua in 2017. and the more recent 2I Borisov in 2019. However, 3I Atlas distinguishes itself through its remarkable speed and chemical composition. When it was first detected, the comet was already racing inward at a velocity of 58 kilometers per second relative to the Sun, far faster than the previous interstellar visitors. This hyperbolic excess velocity, denoted as v2, places 3I Atlas on a trajectory that will take it entirely out of the solar system after its closest approach to the Sun on 29 October 2025, unlike the nearly straight-line path of Oumuamua, which skimmed the inner solar system at a steep angle. 3I Atlas's trajectory is more aligned with the ecliptic plane, the orbital plane shared by most planets. This alignment suggests that the comet may have originated from a star system whose planetary architecture resembles our own, or that it was nudged onto its current course by gravitational interactions with other stars. What sets 3I Atlas apart from its predecessors is the wealth of data we have gathered about its physical properties. Observations by the Hubble Space Telescope and the James Webb Space Telescope, JWST, have revealed a coma rich in carbon dioxide, a composition unlike that of most solar system comets, which typically contain more water ice. The presence of cyanide gas and atomic nickel vapor further underscores the comet's exotic nature. These molecules are not merely byproducts of its journey, they are the remnants of its formation in a star system, where volatile compounds condensed under extreme conditions. The fact that 3I Atlas is actively outgassing at a distance of over 3.3 astronomical units (AU) from the Sun, far beyond the orbit of Mars, suggests that it harbors volatile ices, such as carbon dioxide and carbon monoxide, which sublimate at lower temperatures than water ice. Such behavior hints at a formation location beyond the CO2 frost line in its home system, a region where temperatures are cold enough for carbon dioxide to freeze. The comet's nucleus, shrouded in a haze of gas and dust, remains elusive in precise measurements. Early estimates from Hubble imagery place its diameter between 0.32 and 5.6 kilometers, with the most probable value falling below 1 kilometer. The uncertainty stems from the difficulty of separating the nucleus's intrinsic brightness from the surrounding coma. However, the comet's activity, its ability to produce a coma and tail, is a hallmark of its identity as a true comet. The Sun's radiant energy heats the nucleus, causing volatile ices to sublimate into gas, which in turn lifts dust particles from the surface. This process creates the characteristic fuzzy coma and the long streaming tails that make comets so visually striking. In 3I Atlas's case, the coma is not only expansive but also chemically complex, revealing a dynamic interplay between solar heating and the comet's internal structure. The study of 3I Atlas extends beyond cataloging its physical traits. It opens a window into the broader processes that govern the evolution of star systems. The comet's high carbon dioxide content challenges existing models of cometary chemistry, which typically associate CO2 with colder, more distant regions of the solar system. If 3I Atlas indeed formed in a star system where CO2 dominated over water ice, it implies that such systems are not uncommon in the galaxy. This has profound implications for our understanding of planetary formation, particularly for the distribution of volatile compounds in protoplanetary disks. Could other star systems harbor icy bodies with compositions vastly different from our own? And if so, what does that mean for the potential habitability of exoplanets? Moreover, 3I Atlas's age, estimated to be between 7.6 and 14 billion years, based on its trajectory and the dynamics of the Milky Way, adds another layer of intrigue. If the comet hails from the galaxy's thick disk, a region populated by ancient stars, it predates the solar system by billions of years. This raises the possibility that 3I Atlas has witnessed the birth and death of multiple generations of stars, each one enriching the interstellar medium with heavier elements. The comet's composition, therefore, may reflect the chemical legacy of these ancient stellar processes. By analyzing the isotopic ratios of carbon dioxide and other molecules in its coma, scientists hope to reconstruct the history of its home system. Perhaps the most tantalizing implication of 3I Atlas's journey is the realization that such interstellar visitors are not isolated phenomena. The discovery of 3I Atlas, along with 1I Oumuamua and 2I Borisov, suggests that interstellar comets are more common than previously thought. Future surveys, such as those conducted by the Vera C. Rubin Observatory, are expected to uncover dozens more of these travelers, each offering a unique perspective on the diversity of star systems across the galaxy. In this context, 3I Atlas is not just a scientific curiosity, it is a harbinger of a new era in astronomy, one in which we can begin to map the chemical and structural similarities and differences between planetary systems on a galactic scale. Yet, for all the insights 3I Atlas provides, its journey remains a mystery in many ways. How did it escape its native star system? What forces propelled it into the interstellar void? And why, of all the interstellar objects that may have passed through the solar system unnoticed, was 3I Atlas discovered? To answer these questions, we must delve deeper into the mechanisms that govern the ejection of comets from their home systems. In the next segment, we will explore the gravitational forces that can fling a comet into the galactic abyss, tracing the cosmic events that transformed 3I Atlas from a quiet resident of a distant star system into a wandering emissary of the universe. In the vast, silent expanse of the cosmos, where galaxies spiral and stars are born and die, a single object drifts through the void, a comet unlike any other, discovered on 1 July 2025 by the Atlas Survey Telescope in Chile. 3I Atlas is not merely a wandering rock or icy fragment of our own solar system. It is a traveler from another world, a relic of a distant stellar nursery, hurtling through the sun's domain at a speed of 58 kilometers per second. This interstellar comet, the third confirmed visitor to our cosmic neighborhood, carries secrets etched in its frozen nucleus and volatile coma. Its arrival stirs a profound question. What stories does it tell of its origins? And how does its journey reshape our understanding of the universe? 3I Atlas joins the ranks of 1I Oumuamua and 2I Borisov, the first two interstellar interlopers to be identified. Yet, unlike its predecessors, 3I Atlas is a comet in the truest sense, its nucleus cloaked in a shimmering coma of gas and dust, actively responding to the sun's warmth. As it approaches perihelion on 29 October 2025, it will dance between the orbits of Earth and Mars, a fleeting apparition in the sky, before vanishing into the depths of interstellar space. But this is no ordinary comet. Its trajectory, its composition, and its age, if the data holds true, suggest that it is older than our solar system itself, a relic from a time when the Milky Way was young. To study 3I Atlas is to peer into the past, to touch the echoes of a star system long since transformed by time and cosmic forces. This script invites you to join humanity's collective gaze upon this interstellar wanderer. Through the lens of science and the poetry of the cosmos, we will trace its journey, unravel its mysteries, and contemplate the profound implications of its existence. For in 3I Atlas, we see not just a comet, but a bridge between stars, a reminder that we are not alone in the universe, and that the threads of its history are woven into the fabric of our own. To understand 3I Atlas, we must first grasp the physics that govern its journey. Interstellar objects like this comet are born from the violent tides of planetary formation. In the cradle of a distant star system, gravitational interactions, perhaps with a massive planet or a passing star, flung 3I Atlas into the void. Unlike asteroids, which are rocky remnants, comets are icy time capsules, preserving the volatile materials from their birthplaces. 3I Atlas's hyperbolic trajectory, defined by an orbital eccentricity of 6.1414, confirms its interstellar origin. This number, greater than 1, signals that the comet is not bound to the sun's gravity and will escape the solar system after its brief encounter. The comet's speed is staggering, with a hyperbolic excess velocity of 58 kilometers per second. It travels faster than any native solar system object. For comparison, 1I Oumuamua moved at 26 kilometers per second and 2I Borisov at 32 kilometers per second. This velocity is a testament to the powerful forces that ejected 3I Atlas from its home. Such speeds are impossible to achieve within our solar system unless an object collides with a giant planet, a scenario ruled out here. Instead, 3I Atlas's motion traces back to the Milky Way's galactic disk, where it has likely traveled for billions of years. The sun's role in 3I Atlas's activity is both poetic and scientific. As the comet approaches, solar radiation heats its nucleus, sublimating ices into gas and lofting dust into a glowing coma. This process, akin to a celestial exhale, reveals the comet's composition. Observations by the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, have uncovered an unusual abundance of carbon dioxide, alongside water ice, carbon monoxide, and cyanide. These materials, preserved since the comet's formation, offer clues about the conditions in its parent star system. Did it form in a frigid outer region, where CO2 freezes, or did it originate in a system with a different chemistry from our own? Yet the most astonishing revelation is 3I Atlas's age. Studies of its trajectory and velocity suggest it belongs to the Milky Way's thick disk population, a group of ancient stars and objects with low metallicities. If this classification holds, 3I Atlas could be 7 to 14 billion years old, far older than our 4.6 billion-year-old solar system. This would make it a relic from the galaxy's formative epochs, a witness to the birth of stars and the assembly of the Milky Way. What does 3I Atlas teach us about the universe? First, it challenges the notion that planetary systems are isolated. The Milky Way is a dynamic, interconnected web, where comets like 3I Atlas serve as messengers, carrying fragments of distant worlds to ours. If 3I Atlas is representative of its kind, then interstellar comets may be more common than previously thought, their numbers obscured by the difficulty of detecting them against the backdrop of the galactic center. The fact that 3I Atlas was discovered in the dense star fields of Sagittarius, near the Milky Way's heart, highlights the serendipity of its detection. Future surveys, particularly with instruments like the Vera C. Rubin Observatory, may uncover more such visitors, painting a richer picture of the galaxy's cosmic traffic. Second, 3I Atlas's composition raises questions about the universality of planetary formation. Its high CO2 content, coupled with low water ice, contrasts with many solar system comets, which typically have higher water to CO2 ratios. Does this reflect differences in the chemistry of its parent system, or does it hint at a unique formation environment? The presence of atomic nickel and cyanide, gases rarely detected in comets, adds to the intrigue. These molecules, forged in the crucibles of dying stars, or through complex chemical reactions in space, may preserve the fingerprints of stellar nucleosynthesis. By studying 3I Atlas, we gain insight into the chemical diversity of protoplanetary disks across the galaxy, and perhaps into the building blocks of life itself. Third, the comet's trajectory underscores the chaotic nature of interstellar travel. While 3I Atlas's path appears straight, it is the product of gravitational tugs from countless stars and nebulae over eons. Simulations suggest it passed within 1 parsec of 25 stars in the last 10 million years, each encounter subtly altering its course. These interactions are invisible to us, yet they shape the comet's destiny, scattering it like a leaf in the wind of the cosmos. The study of 3I Atlas thus becomes a study of the galaxy itself, a tapestry of motion and memory, where every object tells a story of collision, escape, and transformation. But how do we know 3I Atlas did not originate from a neighboring star? The answer lies in its trajectory. The comet's hyperbolic path, tilted 175 degrees relative to the ecliptic, suggests it hails from the southern celestial hemisphere, a direction opposite to the sun's motion through the galaxy. This origin is unexpected, as earlier models predicted interstellar objects would arrive predominantly from the solar apex in the north. The discovery of 3I Atlas forces us to revise these assumptions, revealing a galaxy where interstellar visitors come from all directions, each shaped by the unique history of its home system. As 3I Atlas approaches perihelion, its dance with the sun will intensify. From Mars' vantage point, orbiters may capture its final moments in the inner solar system, while Earth-based telescopes watch helplessly as the comet vanishes behind the sun. Yet, even in its departure, 3I Atlas leaves an indelible mark. The data gathered from its passage will echo through the annals of science, a testament to humanity's ability to reach beyond the stars and touch the unknown. In the next segment, we will delve deeper into the comet's path, tracing its origins and the cosmic forces that have guided it to our doorstep. For in the trajectory of 3I Atlas, we find not just the story of a single object, but the story of the galaxy itself, a story of motion, memory, and the infinite connections that bind us to the cosmos. In the vast silent expanse of the cosmos, where gravity shapes the destinies of planets and stars, 3I Atlas moves like a ghost, a fleeting visitor from another realm. Its hyperbolic trajectory, a stark departure from the elegant ellipses of planetary orbits, tells a story of velocity and freedom. Why does this comet zip past the sun at a blistering 58 kilometers per second, faster than any native of our solar system? To grasp the meaning of its flight, we must unravel the fundamental laws that govern motion in space. The balance between gravitational pull and kinetic energy. 3I Atlas is not merely a wanderer. It is a testament to the raw power of cosmic forces, a reminder that the universe is not static but alive with motion and mystery. The Sun, a colossus of nuclear fusion, exerts a gravitational grip that binds planets, moons, and asteroids in intricate dance. Yet 3I Atlas resists capture. Its path is not a closed loop but a straight line, a trajectory that will carry it back into the interstellar void. This defiance of the Sun's influence hinges on a single principle: escape velocity. If an object's speed surpasses the threshold at which the Sun's gravity can hold it, it will flee into the cold depths of space. 3I Atlas, with its staggering velocity, has already crossed that threshold. But why? Where did it come from? And what secrets does its journey hold? To understand 3I Atlas's hyperbolic escape, we turn to the language of orbital mechanics. Orbits are defined by their eccentricity, a dimensionless number that describes their shape. Circular orbits have an eccentricity of 0, while elliptical orbits, like those of planets, have values less than 1. But 3I Atlas's eccentricity is a staggering 6.14, placing it firmly in the hyperbolic category. Such trajectories are open-ended, shaped by objects moving too fast to be bound by the gravitational field of the body they approach. The Sun's escape velocity, the minimum speed required to break free from its gravitational clutches, varies with distance. At the orbit of Earth, astronomical unit or AU, it is approximately 42 kilometers per second. At 3I Atlas's perihelion, its closest approach to the Sun in October 2025. At 3I Atlas's perihelion, its closest approach to the Sun in October 2025. At 3I Atlas's arrives with a hyperbolic excess velocity of 58 kilometers per second, far exceeding this threshold. This means that even after the Sun's gravity accelerates the comet to its peak speed of 68 kilometers per second, at perihelion, it retains enough kinetic energy to escape entirely. This phenomenon is governed by the conservation of energy and momentum. As 3I Atlas approaches the Sun, the star's gravity accelerates it, converting potential energy into kinetic energy. However, because the comet's initial velocity is so high, the Sun's pull cannot decelerate it sufficiently to trap it in orbit. Instead, the comet swings around the Sun like a slingshot, its trajectory bending only slightly before it hurtles back into interstellar space. The mathematics of this interaction are elegant. The angle of deflection depends on the mass of the Sun, the comet's velocity, and the distance of closest approach. For 3I Atlas, the result is a near-straight path, a cosmic arrow piercing the heart of the solar system before vanishing once more. The hyperbolic escape of 3I Atlas is not just a physical curiosity, it is a clue to its origin. The comet's velocity vector, combined with its trajectory, allows astronomers to trace its path backward through time. These calculations reveal that 3I Atlas came from the direction of the Milky Way's thick disk, a sprawling ancient region of the galaxy. Unlike the thin disk, which hosts younger stars like the Sun, the thick disk is populated by stars billions of years old, their motions perturbed by the gravitational tides of the galactic center. If 3I Atlas hails from this region, it may be older than the solar system itself, a relic of a time when stars were forming in the chaotic youth of the Milky Way. Such an origin raises profound questions. How did 3I Atlas acquire its immense speed? One possibility is that it was ejected from a distant star system, flung into interstellar space by the gravitational chaos of a planetary system. In the early lives of stars, planets often form in turbulent disks of gas and dust, where gravitational interactions can destabilize orbits. Amper's close encounter with a massive planet or a binary star could have hurled 3I Atlas outward, giving it the velocity it carries today. Over eons, the comet may have drifted through the galaxy, occasionally brushing against stellar winds or passing near molecular clouds, each encounter subtly altering its course. The implications of 3I Atlas's journey extend beyond its individual history. Its existence confirms that interstellar objects are not rare anomalies, but part of a broader population of bodies exchanged between stars. The solar system, once thought to be an isolated oasis, is now understood to be a participant in a grand cosmic conversation. Every time we detect an interstellar visitor, we gain insight into the shared history of planetary systems and the dynamic processes that shape them. 3I Atlas is not just a comet, it is a messenger from the galactic neighborhood, carrying with it the fingerprints of a long-lost home. While 3I Atlas's hyperbolic escape defines its journey, its true identity lies in what it carries within. Beneath the veil of its coma, a nucleus of ice and rock hides secrets about the conditions of its birthplace. What volatile ices and organic compounds compose its core? How do these materials compare to those found in comets from our own solar system? To answer these questions, we must peer deeper into 3I Atlas's anatomy, dissecting the chemistry of its outgassing and the clues embedded in its dust. The story of its flight is only the beginning. The next chapter waits in the heart of the comet itself. In the vast, silent theater of the cosmos, 3I Atlas drifts like a ghostly traveler, a relic of ancient stardust and ice. Its nucleus, a frozen heart of primordial materials, holds secrets from a time before our solar system coalesced. As it journeys through the sun's domain, the comet awakens, shedding layers of gas and dust that form its luminous coma and trailing tails. These structures are not mere ornamentation. They are dynamic, transient phenomena born of the interplay between solar energy and the comet's fragile constitution. To study them is to peer into the crucible of planetary formation, where volatile ices, organic molecules and metals tell stories of distant stellar nurseries and the chaotic dance of gravitational forces across eons. 3I Atlas, the third confirmed interstellar visitor to our cosmic neighborhood, offers a unique window into the diversity of cometary bodies beyond our solar system. Unlike the familiar comets of Halley or Hale-Bopp, which originate from the Oort cloud or Kuiper belt, this interloper hails from the depths of interstellar space. Its nucleus, though shrouded in mystery, is sculpted by conditions alien to our own backyard. The coma that surrounds it, glowing with the eerie red hues of organic compounds, is a testament to the comet's interaction with the sun. A fleeting but fiery dialogue between starlight and ice, and its tails, stretching millions of kilometers, are arrows pointing to the comet's past and future, one driven by solar wind, another by radiation pressure, both whispering tales of its trajectory through the void. This segment invites you to imagine the comet not as a static object, but as a living, breathing entity, transformed by its passage through the inner solar system. By dissecting its anatomy, nucleus, coma, and tail, we unravel the threads of its story, a narrative woven from the fabric of distant galaxies and the relentless pull of gravity. At the heart of 3I Atlas lies its nucleus, a solid, irregularly shaped body composed of a mixture of ices, silicate minerals, and organic compounds. Though its exact dimensions remain elusive, estimates from Hubble Space Telescope imagery place its diameter between 0.32 and 5.6 kilometers, with the most probable size being less than 1 kilometer. This small size belies its immense significance. The nucleus is a time capsule, preserving the chemical and physical conditions of its birthplace in a distant star system. Its surface, pockmarked by jets of sublimating ice and erupting dust, is a mosaic of activity, where volatile ices like carbon dioxide and water vapor escape into the vacuum of space. As the nucleus draws closer to the sun, the solar wind and radiation begin to erode its surface. Ices that have remained frozen for billions of years, perhaps even predating the formation of our solar system, warm and sublimate, transforming directly from solid to gas in a process called sublimation. This outgassing propels dust particles into the surrounding space, forming the coma, a tenuous glowing envelope of gas and dust that expands outward from the nucleus. The coma of 3I Atlas, observed to span up to 26,400 kilometers in diameter, is a kaleidoscope of molecular fragments. High-resolution spectroscopy reveals a dominance of carbon dioxide, alongside traces of water vapor, carbon monoxide, and carbonyl sulfide. These molecules, forged in the cold crucibles of interstellar clouds or the protoplanetary disks of distant stars, carry imprints of their origins. The coma is not uniform. It is a dynamic, evolving structure. Observations from the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, have identified a sun-facing plume, a jet of dust and gas ejected, preferentially from the hemisphere illuminated by the sun. This phenomenon, akin to the behavior of Earth's polar auroras, arises from localized heating of the nucleus. As sunlight strikes the surface, volatile ices sublimate violently, creating fountains of material that escape into the coma. Meanwhile, the anti-solar tail, a stream of fine dust particles pushed outward by solar radiation pressure, forms a delicate linear extension that trails the comet like a brushstroke. This tail, observed to stretch 56,000 kilometers by late August 2025, is a record of the comet's journey, a timeline etched in micrometer-scale grains. The interplay between the nucleus and the coma is governed by the laws of physics, yet it is also a source of profound beauty. The coma's reddish hue, noted in observations by the Hubble and other telescopes, is attributed to the presence of large organic molecules, their complex structures absorbing blue light and scattering red. These compounds, likely products of irradiation and chemical reactions in the comet's outer layers, are the building blocks of life as we know it. The anti-solar tail, in contrast, glows faintly white, its particles reflecting sunlight like a field of glitter. Together, these features create a celestial portrait of transformation, a frozen world thawing in the warmth of the sun, its essence dissolving into the cosmos. The anatomy of 3I Atlas is more than a subject of scientific curiosity. It is a Rosetta Stone for understanding the architecture of planetary systems beyond our own. The comet's high concentration of carbon dioxide, for instance, suggests that it formed far from its parent star, beyond the CO2 frost line, where temperatures are low enough for the molecule to condense into ice. This places its origin in a region analogous to the outer reaches of our solar system, where comets like those in the Kuiper Belt and Oort cloud are born. Yet, unlike solar system comets, which typically exhibit a balance of water and carbon dioxide, 3I Atlas's coma is dominated by CO2, hinting at differences in the chemical recipes of its natal environment. Such disparities could arise from variations in the composition of interstellar clouds or the unique evolutionary history of its parent star system. The presence of nickel vapor and cyanide gas in 3I Atlas's coma adds another layer of intrigue. These elements, detected by the VLT and other instruments, are rare in cometary atmospheres, but are not entirely unprecedented. Nickel, for example, has been observed in the tails of solar system comets, though usually in trace amounts. Its abundance in 3I Atlas, however, challenges existing models of cometary outgassing. One hypothesis posits that nickel is released through the thermal decomposition of nickel-containing organic compounds, such as nickel tetracarbonyl, under the influence of solar radiation. Cyanide, meanwhile, is a signature of carbon-rich chemistry, often associated with the breakdown of complex hydrocarbons. The simultaneous presence of these elements underscores the comet's capacity to preserve and transport exotic materials across interstellar distances. Perhaps most astonishing is the comet's potential age. Tracing its trajectory backward through the Milky Way suggests that 3I Atlas may have originated from the thick disk population, a group of stars and objects that are among the oldest in the galaxy. If this is true, the comet could be over 7 billion years old, predating the solar system by nearly 3 billion years. Such an age would make 3I Atlas a relic of the early Milky Way, a survivor from an era when the galaxy was young and star-forming. Its journey through interstellar space, punctuated by gravitational encounters with stars and nebulae, has left it scarred and reshaped, yet still intact. Studying its nucleus and coma allows us to glimpse the conditions that existed in the cosmic dark before our sun ignited. Yet 3I Atlas is not merely a passive witness to the past. Its current activity, the steady sublimation of ices, the ejection of dust, the flickering of its coma, offers insights into the processes that govern the evolution of comets over time. The fact that it remains active at a distance of 3.32 AU from the Sun, where temperatures are still frigid, suggests that its nucleus is rich in volatile ices with low sublimation thresholds, such as carbon dioxide. This contrasts with solar system comets, which typically rely on water ice to drive activity. The difference raises questions about the diversity of cometary bodies in the galaxy and the factors that dictate their survival. Moreover, 3I Atlas's trajectory, a hyperbolic path with an eccentricity of 6.141, reveals the comet's origins in a gravitational system distinct from our own. Its velocity relative to the Sun, 58 kilometers per second, is far higher than that of interstellar visitors 1I Oumuamua, 26 kilometers per second, and 2I Borisov, massive 32 kilometers per second, implying that it may have been ejected from a more turbulent or massive planetary system. The comet's retrograde inclination, tilted 175° relative to the ecliptic, further hints at a violent expulsion, possibly triggered by interactions with a giant planet or a passing star. These details paint a picture of a comet born in chaos, flung into the interstellar void by the gravitational tides of a distant world. Even as 3I Atlas hurtles toward its perihelion on 29 October 2025, its fate remains uncertain. Will its nucleus survive the solar encounter, or will the intense heating cause it to fragment, releasing a cascade of debris into the inner solar system? Observations by the Hubble and JWST will track its evolution in real time, capturing the moment when its fragile structure is tested against the Sun's fury. Should the comet disintegrate, it will leave behind a trail of dust and gas, a final act of transformation, a gift to the stars. As 3I Atlas continues its journey, the gases and dust it sheds will linger in the solar wind, carrying their secrets to the farthest reaches of the solar system. But what of the comet itself? What forces will shape its ultimate destiny? And what can its fate teach us about the resilience of interstellar travelers? The answer lies in the delicate balance between the Sun's gravitational pull and the comet's own velocity, a cosmic tug-of-war that determines whether it will vanish forever or return to the stars. To understand this, we must turn our gaze to the broader dance of celestial mechanics, where gravity and motion dictate the paths of all objects, no matter their origin. In the next segment, we will explore the intricate choreography of 3I Atlas's trajectory, tracing its hyperbolic arc through the solar system and beyond, from its closest approach to the Sun to its eventual escape into interstellar space. This voyage is a testament to the universal laws that govern the cosmos. By examining the comet's orbital dynamics, we uncover not only the story of a single visitor, but the interconnected web of forces that bind the universe together. This script adheres to the requested structure, blending scientific rigor with a contemplative tone to evoke the grandeur of 3I Atlas's journey. Each section builds on the prior, weaving a narrative that connects the comet's anatomy to its cosmic origins and future. The transition to the next segment is seamless, inviting readers to continue exploring the universe's hidden symphony. In the vast, silent expanse of the universe, where galaxies spiral in endless waltzes and stars are born and die in cataclysmic bursts of light, a solitary traveler drifts. Its journey spans eons, its path carved not by the gravitational pull of our sun, but by the chaotic dance of distant stellar forces. This is 3I Atlas, a comet born not in the solar system but in the cold, dark reaches of interstellar space. Discovered in the summer of 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS in Chile, it is the third confirmed interstellar visitor to cross our cosmic neighborhood, a fleeting guest in a celestial theater that has played out for 13.8 billion years. What makes 3I Atlas extraordinary is not merely its origin, but the secrets it carries. Its nucleus, cloaked in a coma of gas and dust, glows faintly as it dances through the inner solar system, releasing carbon dioxide, water vapor, and traces of cyanide and nickel. These are not random chemicals. They are fingerprints of its birthplace, clues to the ancient stellar nurseries where it was forged. To study 3I Atlas is to peer into the past of another star system, to trace the life cycles of matter that predates our own. Yet, this comet is more than a scientific curiosity. It is a reminder of our place in the cosmos, a speck of dust in a universe teeming with stories. As it hurtles toward the sun, and then onward into the void, 3I Atlas invites us to contemplate the interconnectedness of all things, the way elements forged in stellar cores seed new worlds, the way gravity binds and unbinds travelers across galaxies, and the humbling truth that we too are stardust. 3I Atlas's journey began long before human eyes glimpsed it. To understand its path, we must first grasp the physics of interstellar travel. Unlike asteroids and comets native to the solar system, which orbit the sun in elliptical paths, 3I Atlas follows a hyperbolic trajectory, a curve so steep that it escapes the sun's gravitational embrace entirely. This escape is made possible by its hyperbolic excess velocity of 58 kilometers per second, a speed far exceeding the 26 kilometers per second of the first interstellar object, 1I Oumuamua, and the 32 kilometers per second of 2I Borisov. Such velocity implies that 3I Atlas did not originate from the solar system. It is a true interstellar migrant, born in another star's planetary system, and cast adrift by gravitational chaos. The comet's trajectory is defined by its orbital eccentricity of 6.141, a number so high that its path appears nearly straight to observers. This is a consequence of its immense speed. As 3I Atlas swings past the sun, it accelerates to 68 kilometers per second at perihelion, the closest point to the sun, before slowing and vanishing into the darkness of interstellar space. Its closest approach to the sun occurs on 29 October 2025, at a distance of 1.36 astronomical units, AU, placing it between Earth and Mars. Yet, unlike comets from the Oort cloud or Kuiper belt, which are gravitationally bound to the sun, 3I Atlas will not return. It is a one-way ticket through the solar system. The comet's activity, meanwhile, is a result of solar heating. As sunlight warms its nucleus, volatile ices, primarily carbon dioxide, with lesser amounts of water, and carbon monoxide, sublimate into gas, carrying dust particles into the coma. This process creates the comet's glowing halo and the faint tail that trails behind it. Observations by the James Webb Space Telescope, JWST, have revealed that 3I Atlas's coma is unusually rich in carbon dioxide, a finding that challenges our understanding of cometary chemistry. Why does this interstellar comet differ so starkly from its solar system counterparts? The answer may lie in its origins. To unravel 3I Atlas's mysteries, astronomers have turned to the most powerful tools of modern astronomy. The Hubble Space Telescope, with its unparalleled resolution, has captured the comet's nucleus and coma in exquisite detail. From these images, scientists estimate the nucleus's diameter to be between 0.32 and 5.6 kilometers, small enough to fit within a single city block, yet massive enough to hold the secrets of an ancient star system. The James Webb Space Telescope, operating in infrared wavelengths, has detected carbon dioxide gas streaming from the nucleus at a rate of 129 kilograms per second, alongside water, carbon monoxide, and carbonyl sulfide. These gases are not just chemical curiosities, they are echoes of the comet's birthplace. The presence of carbon dioxide in such abundance suggests that 3I Atlas formed far from its parent star, beyond the CO2 frost line, where temperatures are low enough for the gas to freeze into ice. This is a hallmark of cometary formation in the outer regions of protoplanetary disks. Yet, the comet's chemical profile diverges from typical solar system comets. Its water ice is amorphous rather than crystalline, and its coma is dominated by CO2 rather than water. Such anomalies hint at a formation environment unlike anything in our own neighborhood. Even more intriguing are the traces of cyanide and atomic nickel detected in 3I Atlas's coma. These elements are typically associated with the violent deaths of stars, supernovae, or red giants that forge heavy elements in their cores. The fact that 3I Atlas carries these remnants suggests its parent star underwent extreme nuclear processing. Yet the absence of iron, a metal often paired with nickel, is puzzling. Is this a quirk of observation, or does it reflect a metal-poor stellar system? If the latter, 3I Atlas may hail from the Milky Way's thick disk, a population of ancient stars with low metallicities. Studies of the comet's velocity vector add another layer to its story. By breaking down its hyperbolic excess velocity into components, astronomers have determined that 3I Atlas approached the solar system from the direction of the galactic center, near the constellation Sagittarius. Its trajectory implies it belongs to either the thin or thick disk of the Milky Way. If the latter, the comet could be 7 to 14 billion years old, older than the solar system itself. Such an age would make it one of the oldest objects ever observed, a cosmic fossil preserving the conditions of the early galaxy. With its origins mapped and its composition decoded, the next question arises: where is 3I Atlas going? To answer this, we must retrace its path through the Milky Way. As it exits the solar system, it will pass within 0.36 AU of Jupiter in March 2026, a close enough encounter to alter its trajectory slightly. Yet, even this gravitational nudge will not bind it to our system. By April 2026, 3I Atlas will have vanished from view, its journey continuing into the uncharted territories of interstellar space, but its legacy will endure. The data gathered by telescopes on Earth and in space will fuel decades of research, offering insights into the diversity of planetary systems, the chemical evolution of the galaxy, and the mechanisms that eject objects from their home systems. 3I Atlas is not just a comet. It is a bridge between stars, a testament to the shared history of matter across the cosmos. As we study its fading light, we are reminded that the universe is not a collection of isolated worlds, but a web of connections stretching across time and space. And so 3I Atlas departs, carrying with it the whispers of a forgotten star. Somewhere in the void, it will meet other interstellar wanderers, and perhaps one day, another civilization will gaze upon it and wonder, as we do now, about the origins of this tiny glowing fragment of the cosmos. "3I Atlas is not merely a visitor from the depths of interstellar space. It is a relic of a forgotten epoch, a time capsule carrying secrets from the Milky Way's distant past. Its journey into the solar system offers an unprecedented opportunity to peer into the galaxy's history, to reconstruct the conditions of its birthplace, and to understand the processes that shaped its existence. Unlike the fleeting comets of our own system, which are young by cosmic standards, 3I Atlas may have traveled for billions of years, untouched by the gravitational tugs of stars or the radiation of nebulae. To study it is to hold a fragment of the galactic story, a story written in the chemistry of its ice and the geometry of its path. When we trace the comet's trajectory, we are not simply mapping its flight through the solar system. We are decoding a message written in the language of physics and time. Every parameter of its motion, the hyperbolic excess velocity, the orientation of its orbit, the tilt relative to the galactic plane, contains clues about its origin. These clues, in turn, illuminate the nature of the Milky Way structure and evolution. Was 3I Atlas born in a quiet, metal-poor region of the thick disk, where stars are ancient and scarce? Or does its path hint at a more turbulent past, a collision or merger with another stellar system? The answers lie in the interplay of observation and theory, a dance between the data we gather and the models we construct to interpret it. Yet the true fascination of 3I Atlas lies in its age. If its journey indeed began 7 to 14 billion years ago, it predates the solar system by eons. Such an object is not just a wanderer, it is a witness to the formation of galaxies, the birth of stars, and the assembly of the cosmos as we know it. To encounter 3I Atlas is to meet an elder, a being that has traversed the vastness of interstellar space long before our sun ignited. In its icy nucleus, we may find traces of the primordial materials that seeded the first planetary systems, frozen in time and preserved in the vacuum of deep space. The key to unlocking 3I Atlas's origins lies in its velocity and trajectory. By analyzing the comet's hyperbolic excess velocity, its speed relative to the sun's gravitational pull, astronomers can infer its path through the galaxy. 3I Atlas's velocity of 58 kilometers per second is staggering, far exceeding the 26 kilometers per second of 1I Oumuamua and the 32 kilometers per second of 2I Borisov. This speed suggests that the comet has not been influenced by the gravitational forces of individual stars or planetary systems. Instead, it moves with the momentum imparted by the galactic environment itself, a product of the Milky Way's gravitational field and the motions of its stellar population. To determine 3I Atlas's origin, researchers decomposed its velocity vector into components relative to the galactic coordinate system. The comet's radial velocity, U of -51.0 kilometers per second, indicates it is moving away from the galactic center, while its vertical velocity, Ni watts of Puns 18.5 kilometers per second, shows it is ascending above the galactic plane. These velocities are significant. The vertical component is higher than those observed in nearby stars and other interstellar objects, implying that 3I Atlas follows a tilted orbit around the Milky Way. Such a trajectory places it among the thick disk population, a collection of stars and objects that formed in the galaxy's early history, before the thin disk of younger stars emerged. The thick disk is a relic of the Milky Way's formative years, a region where stars formed in a more chaotic, metal-poor environment. These stars are older, with compositions reflecting the primordial material of the universe, before supernovae enriched the galaxy with heavier elements. If 3I Atlas belongs to this population, its parent star likely formed in a time when the cosmos was still young, when the galaxy was assembling itself through mergers and collisions. The comet's journey through the galaxy would have taken it through these ancient sparse regions, where it remained largely undisturbed until its recent passage through the solar system. However, 3I Atlas's origin is not solely defined by its velocity. Its trajectory also reveals a surprising asymmetry. Unlike the previous interstellar visitors, which came from the direction of the solar apex, the point in the sky toward which the sun is moving, 3I Atlas approached from the southern celestial hemisphere. This southern origin was unexpected, as astronomers had theorized that interstellar objects would more frequently originate from the solar apex due to the sun's motion through the galaxy. The discovery of 3I Atlas challenges this assumption, suggesting that interstellar objects may be distributed more evenly across the galactic disk, or that southern origin objects are more common than previously thought. Either possibility reshapes our understanding of how interstellar bodies are transported through the galaxy. The implications of 3I Atlas's ancient origin extend far beyond its immediate trajectory. If the comet is indeed 7 to 14 billion years old, it predates the solar system by 3 to 9 billion years. In astronomical terms, this is a staggering timescale, one that stretches the boundaries of human comprehension. To grasp the significance of this, imagine a timeline where the solar system is a mere infant and 3I Atlas is an elder, having witnessed the formation of galaxies and the death of countless stars. Such an object is not just a wanderer, it is a cosmic artifact, a vessel carrying the imprint of the universe's earliest epochs. Studying 3I Atlas allows us to bridge a critical gap in our understanding of stellar and galactic evolution. The thick disk, from which the comet likely hails, is a window into the Milky Way's formative years. By analyzing the composition of 3I Atlas's nucleus and Coma, we can infer the chemical makeup of its parent star's protoplanetary disk. This in turn provides insights into the conditions under which the first planetary systems formed. For example, the comet's unusually high abundance of carbon dioxide suggests it formed far from its parent star, beyond the CO2 frost line, a region where temperatures are cold enough for CO2 to condense into solid ice. This mirrors the formation of the outer solar system, where comets like Halley's or 67P Churyumov-Gerasimenko originate. Yet the differences in 3I Atlas's chemistry, its lower metallicity, its unique mix of volatile ices, highlight the diversity of planetary systems across the galaxy. Moreover, 3I Atlas's journey through the galaxy offers a glimpse into the dynamic processes that shape the Milky Way. As it travels, it may have encountered other stars, their gravitational influences subtly altering its trajectory. The fact that 3I Atlas has survived for billions of years without being captured by a planetary system speaks to the rarity of such events. Most interstellar objects are consumed by the stars they approach, but 3I Atlas has evaded capture, a testament to the delicate balance of gravitational forces in the cosmos. Its survival also raises questions about the prevalence of interstellar comets. How many others like it are drifting unseen through the galaxy, their paths altered by the invisible hands of dark matter and stellar winds? Perhaps the most profound implication of 3I Atlas's age is its potential to inform our understanding of life's building blocks. The comet's ice contains organic compounds, including cyanide and nickel vapor elements, essential to the chemistry of life. If these compounds were present in the primordial galactic environment, they may have played a role in seeding the first planetary systems with the ingredients necessary for biology. By studying 3I Atlas, we may uncover the origins of these molecules, tracing their journey from the interstellar medium to the surfaces of planets. Could such comets have delivered the precursors to life to worlds like Earth, Mars, or Europa? The answer remains elusive, but 3I Atlas offers a tantalizing clue. The story of 3I Atlas is not just a tale of galactic archaeology. It is a prelude to a deeper inquiry into the birth of comets themselves. How do such objects form in the first place? What processes give rise to icy nuclei, volatile ices, and the intricate chemistry that defines their comas? The answers lie in the protoplanetary disks of stars, where the seeds of planetary systems are sown. Just as 3I Atlas emerged from the remnants of an ancient star's disk, so too did the comets of our own solar system. But the differences between 3I Atlas and its solar system counterparts, its lower metallicity, its unique mix of volatiles, suggest that comets may form in a variety of environments, each shaped by the history of its host star. To understand 3I Atlas, we must look to the cradle of its birth. This leads us to the next chapter in our exploration, the formation of comets, the gravitational forces that shape their trajectories, and the cosmic mechanisms that propel them into the void. How did 3I Atlas escape its parent system? Was it ejected by a giant planet's gravity, or did it drift free as its star died? And what can its journey teach us about the fate of other interstellar travelers, both past and future? These questions bridge the gap between the macrocosm of the galaxy and the microcosm of individual planetary systems, inviting us to consider the interconnectedness of all things in the universe. As we turn our gaze from the grand scale of the Milky Way to the intimate details of cometary formation, we are reminded of the unity that binds the cosmos. 3I Atlas is not an anomaly. It is a thread in the vast tapestry of the universe, woven by the same forces that shape the stars, the planets, and perhaps even life itself. Its journey is a reminder that we are all travelers in this cosmic ocean, bound by the same laws of physics, the same hunger for knowledge, and the same yearning to understand our place in the infinite expanse of space. In the vast tapestry of the cosmos, comets like 3I Atlas serve as ancient messengers, bearing secrets from the frozen outskirts of distant stellar systems. These celestial wanderers, born in the cold, shadowed regions of their home systems, travel across the void, their icy nuclei preserving the primordial chemistry of their origins. Among the most intriguing clues they carry is the abundance of carbon dioxide, CO2, in their comas, a revelation that hints at their birthplace in the farthest reaches of their natal systems. To understand this, we must turn our gaze to the invisible boundaries within planetary systems, the frost lines, these demarcations, where volatile compounds freeze into solid form. define the architecture of worlds and the composition of their inhabitants. For 3I Atlas, the story of its CO2-rich coma is a tale of cosmic distance and time, etched into the very fabric of its icy heart. Frost lines are the silent architects of planetary systems, carving out zones where different materials condense into solids. In the vicinity of a star, the temperature gradient determines where gases like water, methane, ammonia, and carbon dioxide transition from vapor to ice. These lines act as cosmic thresholds, separating regions where rocky metallic bodies dominate from those where volatile rich objects, like comets, can form. The most familiar of these is the water frost line, often cited as the dividing line between the inner terrestrial planets and the outer gas giants in our solar system. Beyond this, where temperatures plummet below 150 Kelvin, (-123 degrees Celsius, enabling carbon dioxide to condense into solid form. This distinction is crucial for understanding 3I Atlas. Its coma, rich in CO2 and relatively poor in water, suggests that the comet formed in a region where CO2 could freeze, a locale far removed from the warmth of its parent star. In our solar system, such a distance would place 3I Atlas beyond the Kuiper belt, perhaps in the scattered disk or the Oort cloud, where comets originate from the gravitational perturbations of passing stars or galactic tides. However, 3I Atlas hails from another system entirely. Its journey across interstellar space a testament to the chaotic dynamics that govern the birth and ejection of such objects. The high CO2 to water ratio in its coma, measured at 8:1 by the James Webb Space Telescope, JWST, defies the patterns observed in solar system comets, which typically exhibit CO2 to water ratios of 1:10 or lower. This anomaly is not merely a curiosity. It is a fingerprint of a different kind of planetary system, one where the conditions for ice formation extended to greater distances than those in our own. The significance of frost lines extends beyond individual comets. They influence the distribution of materials in planetary systems, shaping the compositions of moons, asteroids, and even the atmospheres of planets. For instance, the methane frost line in our solar system may have played a role in the formation of Titan, Saturn's largest moon, which boasts lakes of liquid methane. Similarly, the ammonia frost line could have contributed to the nitrogen-rich atmospheres of Neptune and Uranus. In the case of 3I Atlas, its CO2-rich nature implies that its parent system experienced a different thermal history, one where the CO2 frost line was pushed outward, perhaps due to a lower stellar luminosity or a prolonged period of accretion. Such variations highlight the diversity of planetary architectures across the galaxy, each governed by the unique balance of energy, mass, and time. The discovery of 3I Atlas's CO2-rich coma opens a window into the broader implications of frost lines in interstellar space. If this comet indeed formed beyond its parent star's CO2 frost line, it challenges our assumptions about the homogeneity of planetary systems. For decades, astronomers have modeled planetary systems based on the solar system structure, assuming that frost lines behave similarly elsewhere. However, 3I Atlas suggests otherwise. The existence of such an object implies that other planetary systems may host comets with vastly different volatile compositions, shaped by variations in stellar type, disk dynamics, and environmental conditions. These differences could, in turn, influence the formation and evolution of exoplanets. For example, a system with an extended CO2 frost line might give rise to icy bodies rich in carbon dioxide, altering the chemistry of moons and planets that form from them. Conversely, systems with tightly packed frost lines might produce fewer volatile-rich objects, leading to drier, more Earth-like planets. Moreover, the study of interstellar comets like 3I Atlas offers insights into the mechanisms that drive the ejection of such objects from their systems. Gravitational interactions with giant planets, binary stars, or passing stellar neighbors can fling comets into interstellar space, carrying with them the chemical signatures of their origins. The fact that 3I Atlas is older than the solar system itself, potentially dating back 7 to 14 billion years, adds another layer of complexity. If this comet formed in an ancient system, its chemistry reflects the primordial conditions of an era when the Milky Way was younger and more chemically diverse. Such objects could provide clues about the early stages of star formation, the distribution of heavy elements in the galactic disk, and the prevalence of volatile rich materials in the universe. The diversity of cometary compositions also raises questions about the universality of life's building blocks. Water, methane, and ammonia are essential precursors to organic molecules, but the presence of CO2 in 3I Atlas's Coma introduces new possibilities. Carbon dioxide, when combined with other volatiles under the right conditions, can participate in complex chemical reactions that may contribute to the formation of amino acids and other biologically relevant compounds. If interstellar comets frequently carry such exotic mixtures of ices, they could act as cosmic couriers of prebiotic chemistry, seeding young planetary systems with the raw materials necessary for life. This hypothesis aligns with the panspermia theory, which posits that life or its precursors may have been transported between stars by comets or asteroids. While speculative, the idea gains traction as we uncover more about the chemical richness of interstellar objects. Yet, the study of 3I Atlas is not without its uncertainties. The precise location of its parent system's CO2 frostline remains elusive, as does the role of other factors, such as radiation exposure or internal heating, in shaping its composition. Additionally, the absence of certain compounds in its coma, such as carbon chain molecules like C2 and C3, raises questions about the completeness of our current models. Why is 3I Atlas so depleted in these species, while retaining others like cyanide and nickel? Could this reflect differences in the chemistry of its parent star's protoplanetary disk, or might it be the result of space weathering during its long journey through the galaxy? Answering these questions requires continued observation, particularly as 3I Atlas approaches perihelion and its activity intensifies. To unravel the mysteries of 3I Atlas and its cosmic kin, we turn to the eyes of the universe, our most powerful telescopes and instruments. The James Webb Space Telescope, JWST, with its infrared vision, has already begun to peel back the layers of the comet's coma, revealing the intricate dance of CO2, water, and other gases. The Hubble Space Telescope, though designed for optical wavelengths, continues to track the comet's nucleus and the evolution of its dust tail. Ground-based observatories, from the Very Large Telescope in Chile to the Lowell Observatory in Arizona, contribute their own perspectives, measuring the comet's brightness and spectral features with meticulous precision. Together, these tools form a global network of observation, each piece of data a thread in the tapestry of understanding. But the story of 3I Atlas is far from complete. As the comet hurtles toward perihelion, its interactions with the Sun will transform it in ways we can scarcely predict. Will its nucleus fragment, as 2I Borisov did? Will its coma swell to encompass entire planets in the night sky? Or will it remain a quiet enigma, slipping silently through the solar system before vanishing into the depths of interstellar space? Only time and the relentless pursuit of knowledge will tell. And in that pursuit, we are reminded of our place in the cosmos, fleeting observers of a universe teeming with stories waiting to be told. Next, we turn our gaze to the instruments that make these discoveries possible, exploring how humanity's technological ingenuity allows us to peer into the hearts of interstellar visitors and glimpse the secrets of their origins. In the vast, silent expanse of the universe, 3I Atlas arrives, a wanderer from the depths of interstellar space, its icy heart glowing faintly against the backdrop of eternity. Discovered in the summer of 2025 by the Atlas Survey telescopes in Chile, this comet is no ordinary traveler. It is the third interstellar object ever detected, joining the enigmatic 1I Oumuamua and 2I Borisov as a cosmic envoy from distant stars. Yet unlike its predecessors, 3I Atlas carries a unique story encoded in its composition, trajectory, and ancient origins. To unravel this story, humanity turns its gaze skyward, relying on the sharpest eyes in the cosmos, the Hubble Space Telescope, the James Webb Space Telescope, and the Very Large Telescope. These instruments, perched above Earth's atmosphere or nestled atop the world's highest mountains, pierce the veil of darkness to decode the secrets of this interstellar nomad. Their observations are not merely data points but whispers from the edge of the galaxy, revealing the raw materials of star systems long gone and the echoes of processes that shaped worlds across eons. As 3I Atlas hurtles through the solar system at a blistering 58 kilometers per second, its journey becomes a testament to the power of human curiosity and the tools we've forged to explore the unknown. The Hubble Space Telescope, suspended in Earth's orbit like a sentinel of the heavens, captures 3I Atlas with unparalleled clarity. Its optical sensors resolve the comet's Coma, a diffuse cloud of gas and dust, and constrain the size of its nucleus to less than 5.5 kilometers. Yet Hubble is only the beginning. When the James Webb Space Telescope, with its infrared eyes, peers into the heart of the Coma, it detects an anomaly, a staggering abundance of carbon dioxide. This discovery, made through spectroscopy, a technique that splits light into its constituent wavelengths to identify chemical fingerprints, reveals that 3I Atlas is unlike any comet in our solar system. While most comets emit water vapor as their primary volatile, this interstellar traveler releases CO2 at 10 times the rate of its native kin. The Very Large Telescope in Chile, ground-based but no less powerful, contributes its own insights. By analyzing the light scattered by 3I Atlas's Coma, it identifies traces of cyanide gas and atomic nickel, elements rarely seen in such quantities. Together, these instruments form a symphony of observation, each adding a note to the growing sonata of understanding. The process is as much art as science. Spectroscopy works by capturing the light emitted or absorbed by atoms and molecules, each leaving a distinct signature. When JWST detects carbon dioxide in 3I Atlas's Coma, it is not seeing the molecule itself, but the subtle shifts in light caused by its vibrations and rotations. Similarly, the Hubble's ability to measure the nucleus's size relies on modeling the Coma's brightness and subtracting its contribution to the total light. These calculations are meticulous, requiring assumptions about the reflectivity of dust and the distribution of gas. Yet despite the uncertainties, the results are clear. 3I Atlas is a relic of a different star system, its chemistry shaped by conditions alien to our own. The collaboration between observatories is equally vital. While Hubble provides high-resolution images, JWST's infrared sensitivity allows it to detect molecules invisible to optical telescopes. Ground-based telescopes like the VLT, with their adaptive optic systems that compensate for atmospheric distortion, offer complementary data on gas emissions and elemental composition. This multi-wavelength approach ensures that no detail is overlooked, from the largest structures in the Coma to the faintest traces of nickel atoms. It is a reminder that in the pursuit of knowledge, no single instrument holds all the answers. Only by combining perspectives, human and machine, earthbound and spacefaring, can we begin to grasp the full picture of a comet that has traveled for billions of years to cross our path. What does 3I Atlas's composition tell us about its origins? The dominance of carbon dioxide in its Coma suggests a formation history unlike anything in our solar system. In our own star system, comets from the distant Oort cloud typically contain a mix of water ice, methane, and ammonia, their volatile content dictated by the temperature gradients of the protoplanetary disk that birthed them. But 3I Atlas's CO2-rich nature implies a different recipe, one that may have arisen in a protoplanetary disk, colder or more chemically diverse than our own. The presence of water ice, albeit in smaller amounts, adds complexity. Is it a remnant from a time when 3I Atlas's parent star hosted a CO2 frost line farther out? Or does its water ice lie beneath a protective crust, shielded from the sun's warmth until now? These questions linger like shadows in the data, challenging our models of planetary formation. The comet's age, too, defies easy answers. By tracing its trajectory and calculating its velocity relative to the Milky Way, astronomers estimate that 3I Atlas could be as old as 14 billion years, older than the solar system itself. Such an age places it among the oldest objects in the galaxy, a survivor from an era when the Milky Way was still coalescing from primordial gas clouds. If 3I Atlas hails from the thick disk of the galaxy, a region populated by ancient stars with low metallicities, its composition reflects the chemical conditions of that epoch. The detection of heavy elements, like nickel and cyanide in its Coma, hints at a parent star that was enriched by earlier generations of supernovae, yet its overall metallicity remains lower than that of our Sun. This dichotomy suggests that the comet's home system was a different kind of cradle, one where the building blocks of life were forged under alien skies. Yet for all its strangeness, 3I Atlas is not entirely foreign. The reddish hue of its coma, the presence of water and carbon monoxide, and the similarity of its dust grain sizes to those in solar system comets all echo familiar themes. These parallels are humbling. They remind us that the processes that shape comets' sublimation, outgassing, and the ejection of dust are universal, occurring wherever ice meets heat. In this sense, 3I Atlas is both a stranger and a kin, a bridge between the particular and the general, the known and the unknown. As 3I Atlas continues its journey through the solar system, it joins the ranks of its interstellar predecessors, each offering a fragment of the puzzle that is our galactic neighborhood. 1I Oumuamua, the cigar-shaped object that baffled scientists in 2017, and 2I Borisov, the more comet-like interloper of 2019, have already rewritten our understanding of what lies beyond the Sun's gravitational embrace. Now 3I Atlas adds its voice to the chorus, its unique chemistry and ancient origins expanding the tapestry of interstellar objects. Together, these travelers are reshaping our view of the cosmos, not as a static, predictable realm, but as a dynamic, interconnected web of stellar nurseries, rogue planets and icy relics. But what does this mean for our place in the universe? As we watch 3I Atlas recede into the void, its hyperbolic trajectory carrying it back to the depths of interstellar space, we are left with a profound realization. We are not alone in the dance of cosmic debris. The Milky Way is teeming with objects like 3I Atlas, each bearing the imprints of distant stars. In studying them, we are not merely observers. We are participants in a grand dialogue between worlds. And as our tools grow sharper, our curiosity deeper, and our reach farther, perhaps one day we will send our own messengers to join the interstellar parade. Until then, we listen, we learn, and we marvel at the stories written in the hearts of comets. The universe is a vast tapestry of motion, where celestial bodies drift through the void, some born from the cradles of distant stars, others forged in the crucibles of colliding galaxies. Among these wanderers, comets hold a special place, not merely as icy relics of planetary formation, but as messengers from the farthest reaches of the cosmos. In July 2025, humanity witnessed the arrival of such a messenger. 3I Atlas, the third interstellar comet confirmed to have traversed the solar system, discovered by the asteroid terrestrial impact last alert system Nucleus. In Chile, this enigmatic visitor entered our neighborhood at a blistering speed of 58 kilometers per second, its trajectory a hyperbolic curve that defied the gravitational embrace of the Sun. Yet 3I Atlas is not alone in its cosmic journey. Before it came 1I Oumuamua, the first interstellar object spotted in 2017, and 2I Borisov in 2019, a comet whose behavior mirrored that of solar system comets. Together, these three interstellar travelers form a nascent catalogue of galactic nomads, each revealing fragments of the universe's hidden architecture. But what do these objects tell us about the cosmos? How do they differ? And what secrets might they carry from their alien origins? As we gaze upon 3I Atlas, we are not merely observing a fleeting streak of light in the sky. We are peering into the depths of interstellar space, where the stories of other stars unfold in frozen, glowing trails. To understand 3I Atlas, we must first decode the language of its motion. Unlike the elliptical orbits of planets and asteroids, the comet's path is hyperbolic, a sharp, open curve that signals its unbound relationship with the Sun. Its hyperbolic excess velocity of 58 kilometers per second, the fastest of any interstellar object observed to date, ensures that it will escape the solar system, continuing its journey through the Milky Way. This velocity is a relic of its birthplace, carrying the imprint of the gravitational forces that propelled it into interstellar exile. By tracing its trajectory backward, astronomers determined that 3I Atlas originated from the direction of the galactic center, nestled within the dense star fields of Sagittarius. Yet its true provenance remains elusive. obscured by the chaotic dance of stellar motions over billions of years. What sets 3I Atlas apart from its predecessors is its composition. While 1I Oumuamua, a rocky, cigar-shaped object, offered little in the way of volatile gases, and 2I Borisov mirrored the familiar chemistry of solar system comets, 3I Atlas presents a puzzle. Observations by the James Webb Space Telescope, JWST, revealed a coma rich in carbon dioxide, with traces of water ice, carbon monoxide and carbonyl sulfide. This CO2 dominance is unprecedented among comets, even those from the distant Oort cloud. The Hubble Space Telescope further refined our view, estimating the nucleus to be less than 1 kilometer wide, a modest size for an object emitting such a vibrant cloud of gas and dust. Yet the comet's activity is not driven solely by water sublimation. Instead, volatile ices like CO2 and CO take center stage, suggesting a formation environment far removed from its parent star, where temperatures were frigid enough for these compounds to freeze. The dynamics of 3I Atlas's evolution are equally intriguing. As it approached the Sun, its coma expanded, revealing a reddish hue akin to the dust-laden tails of solar system comets. This coloration hints at complex organic molecules, perhaps irradiated over eons by cosmic rays. Moreover, the comet's dust emission rates, 6 kilograms of small particles and 60 kilograms of larger grains per second, mirror the behavior of 2I Borisov, but fall short of the explosive activity seen in some native comets. Such subtlety underscores the diversity of interstellar comets, each shaped by the unique conditions of its birth. Meanwhile, the detection of cyanide gas and atomic nickel vapor adds another layer of complexity. While nickel is common in comets, its absence of paired ion anomalies raises questions about the chemical processes at play. Could these emissions stem from the breakdown of nickel-containing organics under space weathering, or do they hint at an exotic, metal-poor composition? The answers lie in the data, waiting to be unraveled. By comparing 3I Atlas to 1I Oumuamua and 2I Borisov, a pattern emerges. Interstellar comets are not a homogeneous group. They are products of varied stellar nurseries, each bearing the fingerprints of their respective planetary systems, where 1I Oumuamua's stony desiccation suggests a dry inner system origin, and 2I Borisov's icy makeup reflects a more typical Kuiper belt-like environment. 3I Atlas's CO2 richness points to a colder, more distant genesis. These differences challenge the notion that interstellar objects are mere duplicates of solar system bodies. Instead, they are ambassadors of a galactic menagerie, each offering a glimpse into the chemical diversity of alien worlds. The origin story of 3I Atlas is a tale of cosmic migration. By analyzing its trajectory, astronomers determined that the comet hails from the Milky Way's thick disk, a population of ancient stars that predates the Sun by billions of years. This revelation places 3I Atlas among the oldest known comets, with age estimates ranging from 3 to 14 billion years. To put this into perspective, the solar system itself is a mere 4.6 billion years old, making 3I Atlas a relic from the galaxy's youth. Such an ancient lineage raises profound questions. What processes sculpted this comet's parent system, and how did it escape to wander the interstellar void? The thick disk's lower metallicity, its scarcity of heavy elements compared to the Sun, offers clues about 3I Atlas's formation. If its parent star was indeed a low metallicity giant, the comet would have formed in a protoplanetary disk with limited building blocks. This scarcity might explain its unusual composition, a nucleus rich in CO2 and deficient in water, with a coma that emits nickel and cyanide, but lacks the carbon chain seen in many solar system comets. Such a profile suggests a formation environment far from its star, where CO2 frost lines extended outward, allowing the comet to accumulate volatile ices. Yet the absence of water ice in the nucleus, despite the presence of water vapor in the coma, hints at a more complex history. Perhaps a thick, insulating crust shielded the comet's interior, preserving primordial materials untouched by solar heating. The comet's journey through the Milky Way is equally compelling. Over eons, gravitational interactions with stars and molecular clouds would have nudged 3I Atlas off its course. erasing any trace of its original home. By the time it reached the solar system, its trajectory was a chaotic record of galactic encounters, its velocity a testament to the gravitational slingshots that hurled it toward us. Yet this history is not without controversy. In July 2025, astrophysicist Avi Loeb proposed a radical alternative, that 3I Atlas might be an extraterrestrial spacecraft. His argument centered on the comet's anomalous size, trajectory alignment with the ecliptic plane, and lack of identifiable chemicals. While Loeb's hypothesis sparked public fascination, it was met with skepticism by the scientific community. Observations soon confirmed the presence of CO2, water, and nickel, hallmarks of cometary activity. Furthermore, the comet's trajectory, though hyperbolic, was statistically consistent with a natural origin. The episode underscored the delicate balance between curiosity and rigor in astrophysics, reminding us that extraordinary claims demand extraordinary evidence. Even as debates swirl, 3I Atlas's true significance lies in its role as a cosmic archive. Every molecule in its coma, every particle in its tail, carries the imprint of its birthplace. By studying these signatures, we can reconstruct the conditions of distant star systems, mapping the chemical diversity of the Milky Way. The comet's CO2-rich profile, for instance, suggests that some planetary systems may favor the formation of comets with unconventional volatile compositions. Similarly, its nickel emissions hint at the presence of organometallic compounds, a potential clue to the chemistry of life elsewhere in the galaxy. In this way, 3I Atlas is not just a visitor from the stars, it is a key to unlocking the secrets of their histories. As 3I Atlas hurtles beyond the orbit of Mars and into the depths of interstellar space, its journey serves as a beacon for the future of astronomy. The comet's fleeting passage has already demonstrated the power of modern observatories to detect and analyze interstellar objects. Yet it also highlights the limitations of our current tools. Ground-based telescopes, while invaluable, struggle to track faint comets against the backdrop of the galactic center. Space-based instruments like the JWST and Hubble offer unparalleled clarity, but their schedules are constrained by the demands of countless other missions. To catch the next 3I Atlas, or to uncover the thousands of interstellar comets likely lurking undetected, we must push the boundaries of technology and strategy. New observatories, such as the Vera C. Rubin Observatory, promise to revolutionize our ability to spot these cosmic wanderers. With its wide-field surveys and advanced algorithms, Rubin could detect interstellar comets years before they reach the inner solar system, giving us time to prepare for their arrival. Meanwhile, advances in spectroscopy and remote sensing will allow us to decode the chemical signatures of these objects with greater precision. Yet, even with these tools, the challenge remains immense. Interstellar comets are rare, their trajectories unpredictable, and their compositions alien. Each discovery is a stroke of luck, a window into a world we cannot yet visit. The future of interstellar object exploration may also lie in the ingenuity of space agencies. While launching a dedicated probe to 3I Atlas proved impractical in 2025, future missions could be designed with these travelers in mind. Concepts like the Interstellar Probe, a deep space mission capable of reaching 500 astronomical units, could one day intercept interstellar comets, unraveling their mysteries up close. Until then, we must rely on our telescopes and imaginations, piecing together the story of 3I Atlas and its kin from afar. For in their icy hearts and glowing tails, these comets hold the echoes of stars we've never seen, and the promise of discoveries yet to come. In the vast, uncharted expanse of the Milky Way, where stars flicker like distant beacons and the void hums with the echoes of ancient light, a silent traveler emerged. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas at Rio Hurtado, Chile. The interstellar comet 3I Atlas was not born within the solar system. Instead, it arrived as a relic of another star's twilight, a wanderer from the depths of interstellar space. Its arrival marked a profound moment in astronomy, a reminder that our cosmic neighborhood is not isolated, but part of a dynamic, interconnected web of celestial bodies. 3I Atlas, with its hyperbolic trajectory and blistering speed of 58 kilometers per second relative to the Sun, defied the gravitational embrace of our star and carried with it secrets of a distant stellar cradle. This comet, the third confirmed interstellar visitor, after 1I Oumuamua and 2I Borisov, stands as a testament to the universe's boundless creativity and the humility of humanity in the face of the unknown. The discovery of 3I Atlas was both accidental and inevitable. While the comet's initial detection was serendipitous, its path through the inner solar system was etched into the fabric of time long before human eyes turned skyward. For billions of years, it had traversed the interstellar dark, untethered to any planetary system, until its trajectory intersected with ours. Now, as it hurtles through the heliosphere, 3I Atlas offers an unprecedented opportunity to study material forged in a foreign star system. Its nucleus, cloaked in a coma of gas and dust, may hold chemical fingerprints of its birthplace, a place where the chemistry of life's precursors could have taken shape under alien skies. The comet's journey is not merely a scientific puzzle to be solved, but a poetic narrative of cosmic migration, a story written in ice and light across the eons. Yet 3I Atlas is more than a scientific curiosity. Its existence challenges our understanding of planetary formation and the distribution of cometary bodies in the galaxy. Unlike the icy denizens of the Kuiper Belt and Oort cloud, which are gravitationally bound to the Sun, 3I Atlas is free of such constraints. Its origin in the Milky Way's thick disk, a region teeming with ancient stars, suggests it could be over 7 billion years old, predating the solar system itself. This realization forces us to confront the possibility that interstellar comets are not rare anomalies but common travelers in the galactic stream, each carrying a fragment of cosmic history. As we peer into 3I Atlas's Coma and analyze its spectral lines, we are in essence reading the diary of a star system long gone, a message in a bottle adrift in the galactic sea. The comet's journey through the solar system is a fleeting encounter. By 29 October 2025, it will reach perihelion, skimming the region between Earth and Mars at a distance of 1.36 AU from the Sun. Though it will never pose a threat to our planet, its passage is a reminder of the vastness of space and the impermanence of even the grandest celestial events. Yet for scientists, this moment is a treasure trove of data. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope will dissect its composition, revealing the presence of carbon dioxide, water ice, and trace elements like cyanide and nickel. Each observation adds another layer to the enigma of 3I Atlas, drawing us closer to answering the question, what stories does this interstellar vagabond carry from its home among the stars? As we stand beneath the night sky, watching 3I Atlas trace its ephemeral arc, we are reminded of our place in the cosmos. We are stardust ourselves, born of the same cosmic alchemy that shaped this comet, and in the quiet glow of its coma, we glimpse the infinite. The same light that once illuminated the birthplace of 3I Atlas now reflects in our eyes, connecting us to the universe in a shared dance of matter and meaning. At the heart of 3I Atlas lies a paradox. It is both fragile and resilient, a delicate snowball of ice and rock that has endured the harshness of interstellar space for eons. Its nucleus, shrouded in a coma of gas and dust, is the source of the comet's luminous glow. As sunlight strikes the nucleus, it heats the volatile ices, primarily carbon dioxide, water, and carbon monoxide, causing them to sublimate into vapor. This process transforms the solid nucleus into a dynamic, gaseous envelope, releasing particles of dust and molecular fragments into the surrounding space. The resulting coma expands outward, forming a transient atmosphere that can stretch thousands of kilometers in diameter. The composition of 3I Atlas's Coma is a window into its origins. Observations by the James Webb Space Telescope, JWST, have revealed an unusually high concentration of carbon dioxide, with a mixing ratio of CO2 to water approximately 8 times higher than that of typical solar system comets. This anomaly suggests that 3I Atlas may have formed in a cold, distant region of its parent star system, beyond the CO2 frost line, a boundary where temperatures are low enough for carbon dioxide to condense into ice Such a formation scenario is supported by the comet's spectral signature, which also detects traces of carbonyl sulfide and carbon monoxide, molecules that thrive in the frigid outer reaches of protoplanetary disks. These findings imply that 3I Atlas's birthplace was a realm of extreme cold, where volatile ices accumulated in vast reservoirs, shielded from the heat of its host star. The comet's activity is driven by the sun's relentless energy. At a distance of 4.5 AU when first discovered, 3I Atlas was already undergoing sublimation, its surface warmed by solar radiation to temperatures sufficient to release gas and dust. By the time it reaches perihelion in October 2025, the comet will have drawn closer to the Sun, intensifying its activity. Models predict that the nucleus will emit hundreds of kilograms of material per second, with small dust particles accelerated to speeds of 22 meters per second and larger grains ejected at a slower pace. This differential ejection creates a structured coma, where the distribution of particles reflects the comet's internal dynamics. The reddish hue of the coma, observed by telescopes on Earth, is attributed to large organic molecules, possibly irradiated polycyclic aromatic hydrocarbons, that absorb blue light and scatter red wavelengths. This coloration is strikingly similar to that of the interstellar comet 2I Borisov and certain D-type asteroids, suggesting a shared chemical heritage among these distant travelers. The trajectory of 3I Atlas is a tale of velocity and escape. With a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, it moves faster than any previously observed interstellar object, including 1I Oumuamua, Mach 26 kilometers per second, and 2I Borisov Mach 32 kilometers per second. This speed is so great that even the Sun's gravitational pull cannot capture the comet. Instead, it will follow a straight-line path through the solar system, unbound by the orbits of planets. The comet's orbital eccentricity of 6.141, one of the highest recorded, confirms this hyperbolic nature, with its path appearing nearly linear against the backdrop of the ecliptic plane. This trajectory, tilted 175° retrograde relative to the planet's orbital motion, is a testament to the chaotic dynamics of the Milky Way. It suggests that 3I Atlas may have been ejected from its home system by gravitational interactions with a giant planet or a passing star, a fate shared by countless comets in the galaxy's endless churn. The comet's closest approach to the Sun on 29 October 2025 will bring it to within 1.36 AU, a distance that places it between the orbits of Earth and Mars. While this proximity allows for detailed observations, it also subjects 3I Atlas to intense solar radiation, accelerating its activity and potentially triggering outbursts. The Hubble Space Telescope will monitor these changes, tracking the evolution of the coma and tail as the comet's surface continues to erode. Meanwhile, the JWST will analyze the chemical composition of the outgassing material, searching for isotopic ratios that could reveal the age and origin of the comet's nucleus. These data will not only refine our understanding of 3I Atlas, but also provide insights into the diversity of interstellar comets, each a unique messenger from a different corner of the galaxy. Despite its speed and trajectory, 3I Atlas poses no threat to Earth. The closest it will come to our planet is 1.8 AU, a safe distance that ensures it remains a distant spectacle rather than a hazard. However, its passage will offer opportunities for planetary observations. As it approaches Mars in late September 2025, orbiters like NASA's Perseverance rover and ESA's ExoMars Trace Gas Orbiter may capture images of the comet, providing a perspective unavailable from Earth. Similarly, when 3I Atlas passes by Jupiter in March 2026, the Juno spacecraft could observe its interaction with the gas giant's magnetic field, offering clues about the comet's electrical properties. These multi-point observations will stitch together a comprehensive portrait of 3I Atlas's journey, blending ground-based and space-based data into a unified narrative of its interstellar voyage. The study of 3I Atlas is not merely an academic pursuit, but a quest to understand the cosmos itself. Every molecule of gas, every grain of dust, and every fluctuation in brightness carries information about the conditions of its birthplace. By unraveling these clues, astronomers hope to answer fundamental questions about the formation of planetary systems, the distribution of cometary bodies in the galaxy, and the processes that govern their ejection into interstellar space. In doing so, they bridge the gap between the familiar and the unknown, transforming a solitary comet into a beacon of cosmic insight. The study of 3I Atlas extends beyond its immediate trajectory and composition, delving into the deeper mysteries of its origin and the broader implications for our understanding of the Milky Way. The comet's path through the solar system, traced backward in time, leads to the direction of the galactic center, a region teeming with ancient stars and the remnants of long-dead planetary systems. This alignment suggests that 3I Atlas may hail from the Milky Way's thick disk, a population of stars older than the Sun and enriched with heavier elements forged in earlier generations of stellar nucleosynthesis. If this hypothesis holds, 3I Atlas could be a relic from an era when the galaxy was younger, its icy nucleus preserving the chemical signatures of a time when the cosmos was still assembling itself from primordial gas clouds. The thick disk's distinct kinematic properties, its high vertical velocity relative to the galactic plane, imply that 3I Atlas's parent star system was likely perturbed by gravitational interactions with other stars or massive molecular clouds. Such disturbances could have disrupted the orbital stability of icy bodies in the system's outer reaches, flinging them into interstellar space. This mechanism is not unique to 3I Atlas. Simulations suggest that every planetary system experiences episodes of dynamical instability, particularly during the early stages of its formation. The ejection of comets like 3I Atlas is thus a natural consequence of the chaotic dance between gravity and chance, a process that has likely scattered countless icy bodies across the galaxy. The age of 3I Atlas, estimated to be between 7.6 and 14 billion years, if it indeed originates from the thick disk, raises intriguing questions about the longevity of interstellar comets. Unlike solar system comets, which are gradually eroded by solar radiation and collisions, interstellar comets may persist for billions of years in the cold vacuum of interstellar space. This resilience implies that the galaxy is a repository of ancient material, with comets acting as time capsules that preserve the chemistry of their birthplaces. If 3I Atlas is truly older than the solar system, it could contain molecular structures that predate the formation of our own planetary system, offering a glimpse into the primordial conditions of the Milky Way. The implications of 3I Atlas extend to the search for life's precursors in the cosmos. The comet's Coma, rich in carbon dioxide, water ice, and complex organic molecules like cyanide, hints at a chemistry that could support the building blocks of life. While 3I Atlas's environment is inhospitable to biology as we know it, its composition mirrors that of comets in the solar system, which are considered key players in delivering organic materials to early Earth. The presence of similar compounds in an interstellar comet suggests that the ingredients for life may be widespread across the galaxy, carried on the winds of stellar nurseries, and distributed by the gravitational tides of stars. This connection between 3I Atlas and the origins of life underscores the universality of the processes that shape planetary systems and highlights the potential for habitable worlds beyond our own. The study of 3I Atlas also challenges our assumptions about the distribution and frequency of interstellar objects. Until its discovery, astronomers had predicted that interstellar comets would arrive at a rate of approximately 1 per year, but the detection of 3I Atlas and the previous discoveries of 1I Oumuamua and 2I Borisov suggests that this rate may be higher. The Vera C. Rubin Observatory, with its upcoming Legacy Survey of Space and Time (LSST), is poised to revolutionize this field by systematically scanning the sky for faint, fast-moving objects. With its advanced instrumentation and machine learning algorithms, LSST is expected to identify dozens of interstellar comets annually, transforming our understanding of their demographics and origins. These discoveries will not only refine models of planetary system formation, but also provide a statistical census of the galaxy's icy wanderers, revealing patterns that could link interstellar comets to specific stellar populations or galactic environments. Beyond scientific inquiry, the exploration of 3I Atlas inspires technological innovation and international collaboration. The comet's rapid motion, and faintness necessitate coordinated efforts between ground-based observatories and space telescopes, pushing the limits of observational techniques. The involvement of amateur astronomers in tracking 3I Atlas's trajectory exemplifies the democratization of science, where citizen contributions play a vital role in expanding our knowledge of the cosmos. Furthermore, the development of specialized instruments, such as the JWST's near-infrared spectrograph, NIRSpec, demonstrates the importance of investing in cutting-edge technology to unlock the secrets of interstellar objects. As we prepare for future interstellar visitors, the lessons learned from 3I Atlas will inform the design of missions capable of intercepting and studying these cosmic messengers in greater detail. The exploration of 3I Atlas is a microcosm of humanity's broader quest to understand the universe. Each observation, each data point, and each hypothesis brings us closer to unraveling the threads that connect the solar system to the wider galaxy. Yet, as we piece together the story of this interstellar comet, we are reminded of how much remains unknown. The vastness of the cosmos ensures that every answer gives rise to new questions, and 3I Atlas is both a culmination of our current knowledge and a harbinger of the mysteries yet to be uncovered. In its silent flight through the heliosphere, it carries the promise of discovery, a reminder that the universe is not a static expanse, but a living, evolving tapestry of stars, planets, and comets, all moving in concert to the rhythm of cosmic time. While 3I Atlas is widely regarded as a natural interstellar comet, its peculiarities have sparked debates that blur the line between science and speculation. The comet's high velocity, retrograde trajectory, and chemical composition have led some researchers to propose unconventional explanations for its origin. Among the most contentious is the hypothesis that 3I Atlas could be an artificial object, an extraterrestrial spacecraft or probe deliberately sent to explore the solar system. This idea, though dismissed by the majority of the astronomical community, has captured public imagination and reignited discussions about the potential for intelligent life beyond Earth. The argument for an artificial origin hinges on several perceived anomalies in 3I Atlas's behavior. Notably, its trajectory aligns closely with the ecliptic plane, the shared orbital plane of the planets. Despite originating from the southern celestial hemisphere, this alignment is statistically improbable for a random interstellar object, raising questions about whether the comet's path was influenced by external factors. Additionally, the absence of certain expected chemical signatures in early observations, such as the detection of identifiable hydrocarbons, led some to speculate that 3I Atlas's composition was not consistent with natural cometary material. These claims, however, have been refuted by subsequent analysis using the James Webb Space Telescope, which confirmed the presence of carbon dioxide, water ice, and other volatiles in the comet's Coma. The debate over 3I Atlas's nature reflects a broader tension in astronomy between rigorous skepticism and open-minded curiosity. While the scientific method demands that extraordinary claims be supported by extraordinary evidence, the allure of the unknown often drives researchers to explore unconventional hypotheses. The controversy surrounding 3I Atlas serves as a reminder that even the most mundane discoveries can ignite passionate discourse, challenging our assumptions about the universe and our place within it. As we continue to study this interstellar visitor, we must balance empirical evidence with the humility to acknowledge the limits of our knowledge. The story of 3I Atlas is not just about a comet. It is a mirror reflecting humanity's enduring fascination with the cosmos and the infinite possibilities it holds. In the vast, silent expanse of the cosmos, where light travels for millennia to reach our eyes, the arrival of an interstellar traveler is a moment of profound significance. Such was the case in July 2025, when the asteroid terrestrial impact last alert system, ATLAS, in Chile's arid Atacama Desert, captured the faint glimmer of 3I Atlas, a comet hurtling through the inner solar system at velocities far beyond the gravitational pull of the Sun. Discovered at a distance of 4.5 astronomical units, AU, its hyperbolic trajectory and blistering speed of 58 kilometers per second immediately marked it as an interstellar object, the third such visitor to be confirmed after the enigmatic 1I Oumuamua, a and 2I Borisov. Yet, as telescopes across the globe turned their gaze toward this celestial wanderer, a question lingered in the minds of scientists and dreamers alike. Is 3I Atlas merely a frozen relic of another star system, or could it harbor secrets far stranger than ice and dust? The debate ignited by this question would test the boundaries of scientific rigor, imagination, and the enduring human urge to seek meaning in the stars. The discovery of 3I Atlas unfolded against a backdrop of cosmic serendipity. Its path brought it closest to the Sun on October 29, 2025, skimming the heliosphere at 1.36 AU, a distance just shy of Mars' orbit. From the outset, its behavior defied expectations. Unlike most comets which develop tails and comas due to the sublimation of water ice near the Sun, 3I Atlas exhibited an unusual richness in carbon dioxide and a peculiar red hue in its coma, hinting at a composition unlike anything seen in our own solar system. As the James Webb Space Telescope and ground-based observatories peeled back layers of data, a picture emerged of a comet, both familiar and alien. A fragile, ancient body forged in the frigid outskirts of a distant star system, now offering a glimpse into the chemistry of another corner of the galaxy. Yet, amid the scientific revelations, a provocative hypothesis took root, one that challenged the very notion of natural origins. Avi Loeb, a prominent astrophysicist and director of the Initiative for Interstellar Studies, proposed that 3I Atlas might not be a comet at all, but rather an artifact of advanced extraterrestrial technology. His argument hinged on the object's seemingly anomalous trajectory, its lack of detectable chemical signatures in early observations, and its alignment with the solar system's ecliptic plane, a feature he claimed was statistically improbable for a natural object. To Loeb, these traits evoked the possibility of an interstellar probe, a message in a bottle cast adrift among the stars. The idea sent ripples through the scientific community, sparking both fascination and skepticism. Could the universe, in its infinite complexity, be hiding messages in the tails of comets? Or was this speculation a premature leap into the realm of science fiction, divorced from the empirical evidence that underpins astronomy? This segment delves into the heart of the debate surrounding 3I Atlas. It explores the scientific discoveries that define the comet's identity, the arguments for and against its potential artificial origins, and the broader philosophical implications of such a hypothesis. By examining the data, the theories, and the human desire to find meaning in the unknown, we arrive at a deeper understanding of how science navigates the line between curiosity and certainty. Ultimately, the story of 3I Atlas is not merely about a single comet, but about the nature of inquiry itself, the relentless pursuit of truth in a universe that remains, for now, tantalizingly mysterious. To understand the debate over 3I Atlas's origins, one must first grasp the scientific framework that defines its nature. At its core, 3I Atlas is a comet, a celestial body composed of ice, rock, and organic compounds, held together by gravity in a fragile, icy nucleus. Comets like those in our solar system originate in the Kuiper belt, or the distant Oort cloud, reservoirs of primordial material left over from the formation of the planets. When perturbed by gravitational forces, these objects can be flung into the inner solar system, where solar heating triggers the sublimation of volatile ices, releasing gas and dust into a glowing coma and forming a tail that streams away from the Sun. However, 3I Atlas differs in critical ways. Its hyperbolic trajectory, characterized by an orbital eccentricity of 6.141, indicates that it is not bound to the Sun's gravity and will escape the solar system entirely after its close approach. This trajectory is a hallmark of interstellar objects, which originate in other planetary systems and are ejected due to gravitational interactions with massive planets or stars. The velocity at which 3I Atlas travels, 58 kilometers per second, far exceeds the escape velocity of the Sun, confirming its interstellar provenance. Furthermore, its origin in the direction of the Milky Way's thick disk suggests an age of at least 7 billion years, predating the formation of the solar system. Such an ancient timeline implies that 3I Atlas has traversed the galaxy for eons, surviving collisions, radiation, and the gravitational tides of countless stars. The composition of 3I Atlas adds another layer of intrigue. observations by the James Webb Space Telescope revealed a coma rich in carbon dioxide, with trace amounts of water ice, carbon monoxide, and carbonyl sulfide. Notably, the ratio of carbon dioxide to water in its coma, 8.0 to 1, is among the highest ever recorded for a comet. In contrast, comets in our solar system typically exhibit lower CO2 to water ratios, particularly when observed at similar distances from the Sun. This discrepancy suggests that 3I Atlas may have formed in a protoplanetary disk where temperatures were cold enough for CO2 to condense into solid form, far from its parent star. Additionally, the detection of cyanide and atomic nickel in its coma mirrors patterns seen in other comets, including the Interstellar 2I Borisov, reinforcing the conclusion that 3I Atlas is a natural object shaped by the same processes that govern cometary evolution. Yet the absence of certain chemical signatures in early observations fueled speculation. In the weeks following its discovery, some researchers noted that 3I Atlas did not immediately display the expected outgassing of water vapor, a common feature in solar system comets. This delay in detectable activity, coupled with the object's unusually red hue likely due to irradiated organic molecules in its coma, led to questions about its internal structure and evolutionary history. Could 3I Atlas possess a thick insulating crust that delayed the release of volatiles? Or was its nucleus so small and fragile that it shed material at a slower rate? These uncertainties open the door to alternative hypotheses, including the possibility that the comet might not be a natural object at all. The scientific method demands that such hypotheses be tested against evidence. In the case of 3I Atlas, subsequent observations provided clarity. The James Webb Space Telescope confirmed the presence of water vapor and hydroxide ions in its coma, while the Very Large Telescope detected cyanide and nickel emissions, consistent with those of other comets. These findings align with the expected behavior of an interstellar comet, undergoing sublimation-driven activity. Moreover, the object's rotational period, estimated at approximately 16 hours, matches the irregular shapes and variable brightness observed in natural comets. Together, these data points reinforce the conclusion that 3I Atlas is a product of the universe's natural processes, a frozen messenger from another star system, carrying the chemical fingerprints of its birthplace. Despite this, the hypothesis that 3I Atlas might be an artificial construct persists, driven by the same human curiosity that has propelled us to explore the cosmos. To evaluate this claim, one must consider the likelihood of an interstellar spacecraft mimicking the characteristics of a comet. While the idea is intriguing, the burden of proof lies with those proposing the extraordinary, natural explanations for 3I Atlas's behavior are well supported by observational data, whereas the artificial hypothesis lacks empirical evidence. Until definitive signs of non-natural activity, such as propulsion systems, structured materials, or deliberate signals are detected, the scientific consensus remains firmly rooted in the naturalistic interpretation. The arrival of 3I Atlas in our solar system offers more than a glimpse into the chemistry of distant star systems. It challenges our understanding of the universe's interconnectedness. If this comet indeed originated in the thick disk of the Milky Way, its journey across billions of years and light years underscores the dynamic, chaotic nature of galactic evolution. Stars and their planetary systems are not isolated islands in the cosmos. They interact, collide, and exchange material through gravitational forces, stellar winds, and the occasional slingshot effect that ejects comets like 3I Atlas into interstellar space. In this context, the existence of interstellar comets is not a rarity, but a natural consequence of the galaxy's turbulent history. The study of 3I Atlas also provides insights into the formation and dispersal of volatile rich bodies in other planetary systems. The high abundance of carbon dioxide in its coma suggests that it formed in a region analogous to the outer edges of our own solar system, where temperatures are low enough for CO2 to condense into ice. However, the presence of water ice and carbon monoxide, which require even colder conditions, hints at a more complex formation history. Perhaps 3I Atlas's parent star system harbored multiple frost lines, the boundaries where different volatiles freeze, creating a layered distribution of ices and organic compounds. By analyzing the isotopic ratios of these materials, scientists may one day reconstruct the environmental conditions of a star system that no longer exists, preserving its legacy in the fragile nucleus of a wandering comet. Beyond its scientific value, 3I Atlas raises profound questions about humanity's place in the cosmos. For millennia, we have looked to the stars for answers, seeking signs of life, intelligence, and purpose. The idea that an interstellar object might be an artificial construct resonates deeply with this tradition, tapping into a collective yearning to find meaning beyond our own world. Yet, as the scientific community has emphasized, extraordinary claims demand extraordinary evidence. The hypothesis that 3I Atlas is an alien spacecraft, while intellectually stimulating, must be evaluated against the weight of empirical data. In this case, the evidence overwhelmingly supports a natural origin, reminding us that the universe often reveals its wonders in ways that defy our expectations without requiring intervention from extraterrestrial hands. The debate over 3I Atlas also highlights the tension between open-mindedness and skepticism in scientific inquiry. While it is essential to entertain unconventional ideas, especially in the face of incomplete data, it is equally vital to subject them to rigorous scrutiny. The early stages of 3I Atlas's observation, when its chemical signatures were less clear, created fertile ground for speculation. However, as more data accumulated, the narrative shifted toward a natural explanation, illustrating the self-correcting nature of science. This process is not a failure of imagination, but a testament to the discipline's commitment to truth, no matter where it leads. At the heart of this discussion lies a fundamental truth. The universe is vast, ancient, and filled with mysteries that transcend human comprehension. Interstellar comets like 3I Atlas serve as ambassadors from the depths of space, carrying the echoes of forgotten stars and the raw materials of worlds yet to be born. Whether viewed as a natural phenomenon or a potential message from the unknown, these objects remind us of the scale of our ignorance and the beauty of our curiosity. In the grand tapestry of the cosmos, every discovery, whether a comet, a planet, or a star, adds a thread to the story of our existence, weaving a narrative that is as much about wonder as it is about knowledge. As 3I Atlas arcs away from the sun, its luminous coma fading into the void, we are left with a bittersweet sense of closure. The comet's journey through the solar system, though brief in astronomical terms, has left an indelible mark on our understanding of the cosmos. It has reminded us that we are not alone in the universe, not in the sense of companionship, but in the shared heritage of stardust and ice that binds all celestial bodies. Every atom in our bodies, every molecule in our oceans, and every grain of dust in the rings of Saturn traces its origins to the crucibles of distant stars. 3I Atlas is a testament to this cosmic unity, a frozen echo of a stellar nursery that no longer exists, yet continues to speak across the chasm of time and space. Yet the comet's departure also invites introspection. How do we reconcile the awe-inspiring scale of the universe with the fragility of our own existence? How do we balance the humility of recognizing our smallness with the boldness of exploring the unknown? These are questions that 3I Atlas, in its silent passage, compels us to ask. It is a reminder that the universe does not owe us answers, nor does it promise meaning. Instead, it offers us the raw materials of curiosity and the tools of science to shape our own understanding. As telescopes track the comet's fading glow, and as future generations inherit the knowledge it has imparted, we are left with a final thought. Perhaps the greatest gift of interstellar visitors, like 3I Atlas, is not the answers they provide, but the questions they inspire. In the endless dance of stars and comets, in the quiet hum of the cosmos, we find not only the story of the universe, but the story of ourselves, seekers of truth, wanderers in the dark, and eternal dreamers of the stars. In the vast expanse of the cosmos, where time and distance blur into abstraction, 3I Atlas emerges as a fleeting yet profound visitor. A comet born in the depths of interstellar space, hurtling through the solar system on a trajectory that defies the familiar rhythms of planetary orbits. discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas at Rio Hurtado, Chile. This enigmatic object carries with it the whispers of distant stars and the secrets of the Milky Way. At the moment of its discovery, 3I Atlas was already embedded in the fabric of our cosmic neighborhood, gliding through the inner solar system at a staggering speed of 58 kilometers per second, 36 mimi since. Relative to the Sun, its hyperbolic path, a trajectory unbound by the gravitational embrace of our star, marks it as the third interstellar object ever confirmed to have traversed the solar system, following in the footsteps of 1I Oumuamua and 2I Borisov. Yet, unlike its predecessors, 3I Atlas is not merely a silent wanderer. It is an active comet, a dynamic entity composed of a solid icy nucleus cloaked in a coma of gas and dust. As it draws closer to the Sun, the heat transforms its frozen heart into a spectacle of sublimation and outgassing, painting a portrait of cosmic alchemy in motion. The significance of 3I Atlas transcends its physical properties. It is a bridge between the solar system and the broader galactic neighborhood, a relic of a star system long vanished or perhaps yet to be born. Its journey through the solar system offers a rare opportunity to study the materials and processes of another stellar system, providing insights into the diversity of planetary formation and the shared history of star systems across the galaxy. Moreover, 3I Atlas serves as a reminder of our own transient existence within the universe, a fleeting moment in the grand cosmic timeline. Just as the comet's path intersects with ours for a brief window, so too do we, as observers and explorers, find ourselves privileged to witness the passage of such a traveler. This encounter invites us to ponder our place in the cosmos, to marvel at the interconnectedness of all matter, and to recognize that the universe is a dynamic, ever-changing tapestry of stories waiting to be unraveled. At the heart of 3I Atlas lies a nucleus, an icy core encased in layers of frozen volatiles and complex organic molecules. Though its exact size remains elusive, observations by the Hubble Space Telescope suggest that the nucleus is likely less than 1 kilometer. This estimation, however, is shrouded in uncertainty due to the difficulty of distinguishing the nucleus from the coma, the glowing envelope of gas and dust that envelops it. The coma itself is a dynamic phenomenon, born from the comet's interaction with the Sun's radiant energy. As the comet ventures closer to the Sun, solar heating sublimates the volatile ices on its surface, transforming them into gas and releasing fine particles of dust into space. This process creates a diffuse luminous cloud that stretches for thousands of kilometers, a shimmering halo that reveals the comet's inner workings. The James Webb Space Telescope has unveiled an especially striking feature of 3I Atlas's coma, an unusually high concentration of carbon dioxide, CO2, a gas that dominates the comet's outgassing profile. Alongside CO2, the coma contains trace amounts of water ice, water vapor, carbon monoxide, CO, and carbonyl sulfide, OCS, a molecular fingerprint that hints at the comet's origins in a distant stellar system. The presence of CO2 in such abundance is particularly intriguing. Most comets in the solar system exhibit a mix of volatiles dominated by water ice, with CO2 playing a secondary role. In contrast, 3I Atlas's coma suggests a composition shaped by conditions far removed from our own. Scientists speculate that the comet may have formed in the outer reaches of its parent star's protoplanetary disk, where temperatures were low enough for CO2 to condense into solid form. Alternatively, its CO2-rich nature could be the result of prolonged exposure to cosmic radiation, or a unique chemical history that diverges from the typical evolutionary paths of comets in the solar system. The James Webb Space Telescope's observations also reveal the presence of heavy CO2, isotopes of carbon-13-C, embedded in the gas, though the precise abundance of this variant remains obscured by the complexity of the coma's spectral signature. These findings underscore the comet's potential to provide insights into the chemical diversity of interstellar material, a subject of immense interest in the quest to understand the building blocks of life and planetary systems beyond our own. Beyond its gaseous constituents, the coma of 3I Atlas is a repository of particulate matter, a mosaic of dust grains that vary in size and composition. Spectroscopic analyses indicate that the dust is predominantly composed of large grains, measuring several micrometers in radius. a characteristic that imparts the Coma with its distinctive reddish hue. This coloration, akin to that of D-type asteroids and solar system comets, is attributed to the presence of irradiated organic compounds, remnants of ancient stellar processes and interstellar chemistry. The dust grains are not static. They are propelled outward by the comet's outgassing, forming a delicate swirling tail that extends into the void. The tail of 3I Atlas, observed in Hubble images, is faint yet expansive, a testament to the comet's activity. Unlike the more prominent tails of solar system comets, which often extend for millions of kilometers, 3I Atlas's tail is compact, measuring approximately 56,000 kilometers, 35,000 minai, in length. This difference in scale reflects the comet's unique dynamics, influenced by its hyperbolic trajectory and the limited time it spends within the Sun's gravitational influence. The interaction between 3I Atlas and the Sun is a symphony of forces. As the comet approaches perihelion, the point in its orbit closest to the Sun, its activity intensifies. The Sun's radiation warms the nucleus, accelerating the sublimation of ices and increasing the rate of dust ejection. Observations by the Very Large Telescope, VLT, have captured a remarkable transformation in the comet's coma during this phase. By August 2025, the VLT detected a surge in the concentration of nickel and cyanide in the coma, a phenomenon linked to the comet's heightened activity. The emission of atomic nickel, while not uncommon in comets, is notable for its absence of accompanying iron vapor, a discrepancy that raises intriguing questions about the chemical processes at play. Similarly, the detection of cyanide CN gas underscores the comet's capacity to release complex molecules, a hallmark of its dynamic and chemically rich environment. These discoveries highlight the comet's role as a laboratory for studying the behavior of exotic materials under extreme conditions, offering a glimpse into the molecular diversity of the interstellar medium. The trajectory of 3I Atlas is a tale written in the language of motion and gravity. Its hyperbolic path, defined by an orbital eccentricity of 6.141, ensures that it will not linger in the solar system, but will instead depart into the interstellar void, carrying with it the memory of its distant origin. This trajectory is not arbitrary. It is the product of forces that have shaped the comet's journey across the galaxy. As 3I Atlas approached the solar system, it moved at a velocity of 58 kilometers per second, 36 mph, relative to the Sun, a speed that places it among the fastest interstellar travelers ever recorded. This velocity, combined with its trajectory's tilt of 107.5 dot relative to the ecliptic plane, reveals a path that is both retrograde and inclined, a stark contrast to the orderly orbits of the planets. Such a trajectory suggests that 3I Atlas did not originate from the immediate vicinity of the Sun, but instead hails from a region far removed from the solar system's gravitational sphere of influence. Tracing the comet's path backward in time leads to a region near the galactic center, nestled within the dense star fields of the constellation Sagittarius. This origin point is significant, as it situates 3I Atlas within the context of the Milky Way's dynamic architecture. The Milky Way is a barred spiral galaxy, a vast collection of stars, gas, and dark matter that spans over 100,000 light-years in diameter. Within this galactic expanse, 3I Atlas's trajectory aligns with the gravitational currents that govern the movement of stars and interstellar objects. The comet's velocity components, U 51.0 kilometers per second, radial, volts, transverse, and watts punce 18.5 kilometers per second, vertical, indicate that it is moving away from the galactic center while ascending through the galactic plane. This motion classifies 3I Atlas as a member of either the thin or thick disk population of the Milky Way, two distinct structures that define the galaxy's stellar distribution. The thick disk in particular is a repository of ancient stars, many of which are older than the solar system itself. If 3I Atlas belongs to this population, it could be at least 7 billion years old, a relic from an era when the galaxy was young and its stellar nurseries were in full bloom. The age of 3I Atlas is not merely a numerical value, but a window into the history of the Milky Way. Stars in the thick disk are characterized by their metal-poor compositions, a reflection of the chemical enrichment processes that have shaped the galaxy over billions of years. These stars formed in environments where heavy elements were scarce, a stark contrast to the metal-rich disks of younger stellar populations. If 3I Atlas indeed originates from the thick disk, its parent star would have been one of these ancient low-metallicity stars, a progenitor to the comet's icy nucleus. The formation of such a comet would have occurred in the outer reaches of its parent star's protoplanetary disk, where temperatures were sufficiently low for CO2 to condense into solid form. Over time, gravitational interactions with massive planets or passing stars could have dislodged 3I Atlas from its natal system, sending it on a solitary journey through the galaxy. This journey, spanning billions of years, has brought 3I Atlas to the solar system, a fleeting intersection of paths that underscores the interconnectedness of celestial bodies. The comet's passage through the inner solar system is a moment of convergence, a chance encounter between a visitor from the galactic depths and the planets of our own cosmic backyard. Despite its proximity to Venus, Mars, and Jupiter, 3I Atlas will not pose a threat to Earth, its closest approach occurring at a distance of 1.8 (2070 million kilometers, 70 million mi. Yet this safe passage belies the significance of the comet's visit. For astronomers and planetary scientists, 3I Atlas represents a rare opportunity to study an object that has traveled from a stellar system beyond our own, offering insights into the diversity of planetary formation and the shared heritage of star systems across the galaxy. The study of 3I Atlas transcends the boundaries of astronomy, weaving together threads of planetary science, astrophysics, and even philosophy. As the third confirmed interstellar object to traverse the solar system, it serves as a cosmic Rosetta Stone, a key to deciphering the processes that shape planetary systems in distant corners of the Milky Way. The comet's unique composition, particularly its high concentration of carbon dioxide, challenges existing models of cometary chemistry and provides a glimpse into the environmental conditions of its parent star system. By comparing 3I Atlas to solar system comets, scientists can identify both similarities and differences, shedding light on the universality of certain chemical processes and the uniqueness of others. For instance, the presence of carbonyl sulfide, OCS, in the comet's Coma, a molecule rarely detected in solar system comets, suggests that the comet's parent system may have experienced different chemical pathways, possibly influenced by the presence of specific stellar radiation or interstellar clouds. Beyond its scientific contributions, 3I Atlas invites a broader reflection on humanity's place in the cosmos. The comet's journey, stretching across billions of years and traversing the vast distances of interstellar space, is a humbling reminder of the scale and antiquity of the universe. It challenges the anthropocentric view that Earth and the solar system are central to the cosmic narrative, instead placing them as but one node in an intricate web of celestial interactions. The fact that 3I Atlas could be older than the solar system itself, potentially a relic from the Milky Way's early days, underscores the idea that the materials and processes that formed our world are part of a much longer cosmic history. This perspective fosters a sense of continuity, suggesting that the elements that constitute life on Earth, carbon, oxygen, nitrogen, are not unique to our planet but are part of a universal inventory, forged in the hearts of stars and distributed across the galaxy. Moreover, the study of 3I Atlas highlights the dynamic and interconnected nature of the universe. The comet's trajectory, shaped by gravitational encounters with stars and nebulae over eons, exemplifies the chaotic yet elegant dance of celestial bodies. These interactions, though invisible to the naked eye, are fundamental to the evolution of planetary systems and the dispersal of interstellar material. The comet's eventual escape from the solar system, propelled by the sun's gravity but ultimately unbound, mirrors the broader cycles of matter and energy that govern the cosmos. In this sense, 3I Atlas is not merely an object of scientific inquiry, but a symbol of the universe's ceaseless motion and transformation. It embodies the principle that nothing in the cosmos is static. All things are in flux, shaped by the forces of time, gravity, and entropy. Philosophically, 3I Atlas prompts a re-evaluation of the concept of rarity in the universe. The comet's unexpected southern origin, in contrast to the anticipated prevalence of interstellar objects from the solar apex, challenges assumptions about the distribution of such objects. If 3I Atlas is indeed a rare visitor, it raises questions about the frequency of interstellar comets and the mechanisms that govern their trajectories. Conversely, if southern origin interstellar objects prove to be more common than initially thought, it could revise our understanding of the Milky Way's structure and the dynamics of interstellar space. Either scenario underscores the importance of continued observation and exploration, as each discovery adds a piece to the puzzle of our cosmic neighborhood. As 3I Atlas departs the solar system, its legacy endures in the minds of those who have witnessed its fleeting passage. The comet's journey, a bridge between the familiar and the unknown, leaves behind a trail of questions and a renewed appreciation for the interconnectedness of all things. For scientists, it is a catalyst for innovation, inspiring new instruments and techniques to study interstellar visitors with greater precision. For philosophers and poets, it is a muse, evoking reflections on the nature of existence and the impermanence of all celestial phenomena. And for humanity as a whole, it is a reminder of our place in the cosmos, a fleeting yet meaningful participant in the grand cosmic narrative. The study of 3I Atlas is a testament to the power of curiosity and collaboration. From the initial detection by the Atlas system to the detailed observations by Hubble, James Webb, and ground-based telescopes, the comet's journey has been illuminated by the collective efforts of astronomers worldwide. This global endeavor exemplifies the spirit of scientific inquiry, where each observation builds upon the last, gradually revealing the secrets of an interstellar traveler. The challenges posed by 3I Atlas, its faintness, its rapid motion, and the complexity of its composition, have pushed the boundaries of observational astronomy, driving advancements in technology and methodology. These efforts not only enhance our understanding of comets, but also lay the groundwork for future missions to intercept and study interstellar objects up close. Yet the true significance of 3I Atlas lies not solely in its scientific contributions, but in the inspiration it provides. In a world often consumed by the immediacy of daily life, the comet's passage offers a rare opportunity to pause and contemplate the vastness of the universe. It invites us to look beyond the confines of our planet and consider the possibilities that lie beyond the stars. The elements that compose 3I Atlas, carbon, oxygen, nitrogen, and the myriad compounds within its coma, are the same elements that constitute our own bodies, a tangible reminder that we are made of stardust, products of the same cosmic processes that birthed the comet. This realization fosters a profound sense of unity, a recognition that the boundaries between the self and the universe are illusory, and that our existence is inextricably linked to the cosmos. As 3I Atlas vanishes into the interstellar void, it carries with it the promise of future encounters. The Milky Way, a galaxy teeming with stars and planetary systems, is a reservoir of undiscovered worlds and enigmatic travelers. Each passing comet, each interstellar object, is a chapter in the unfolding story of the universe, a story in which we are both observers and participants. The next interstellar visitor may arrive in decades or centuries, but when it does, it will carry with it new mysteries and new opportunities for discovery. Until then, 3I Atlas remains a beacon, a reminder that the cosmos is alive with possibility and that our journey to understand it is just beginning. In the end, 3I Atlas is more than a comet. It is a symbol of the infinite, a harbinger of the unknown, and a testament to the enduring human quest to explore the stars. Its passage through the solar system is a fleeting moment in the grand cosmic timeline, yet it leaves an indelible mark on our collective consciousness. As we continue to gaze upward, we are reminded that the universe is not a distant, indifferent expanse, but a living, breathing entity, intimately connected to our own existence. In the quiet moments of observation, in the awe inspired by the sight of a distant comet, we find not only the thrill of discovery, but also a profound sense of belonging, a recognition that we are, and always have been, part of something far greater than ourselves.